all the models for both regression and classification were equally applicable to data that was first transformed via basis functions. Now in this short video, I'm going to briefly remind you of the usefulness of basis functions, now in the classification setting, but I'm also going to talk a little bit about their limitations. And this will eventually motivate us to make learning of basis functions part of our modeling approach. And this will eventually lead to the formulation of multi-layer perceptrons or neural networks. But first things first, let's take a look at a toy example where basis functions are clearly beneficial. Now suppose we are given this two-dimensional data set. So we have features, like two features, can be anything, and I have two classes. And I want to separate these two classes, so one indicated in red and the other in blue, via a linear classification model, or maybe generalized linear classification model. Then there's no way I'm going to be able to separate these two classes with just a linear classifier, right? So I could draw a decision boundary somewhere over here that will classify this correctly, but then this part won't be classified correctly. And I can try out all sorts of decision boundaries, but none of them would work. Now this is a nice example of where we can use basis functions to turn this into a linear classification problem. So we can design, we can pick basis functions such that the data transforms in the following way, that the blue data points can be clearly separated with a linear decision boundary from the red data points. Now in this particular example, we're going to do that via Gaussian basis functions, where we center a Gaussian function around this point over here and this point over here. So let's say this Gaussian has an average or a mean value mu1, and this particular one has a mean value mu2. So what does that look like? So my first feature value is going to be obtained by mapping this point x through this first basis function. And this first basis function was a Gaussian basis function, so that means an exponential to the power of minus a half x minus mu1, so the distance to the first center, x minus mu2. And then I have this second basis function, phi2 of x, which essentially computes the affinity or closeness of a data point x to the second mean. Okay, so that's the second basis function. It's also a Gaussian basis function. And that's how we could interpret this, right? So this basis function, essentially, what's happened inside this exponential is I'm going to compute the distance from a point x to this mu, and I'm going to pull this through this exponential. So whenever this distance is small, this exponential will have a large value. And whenever this distance is large, for example, points over here have a large distance to this mean, then e to the power of minus something large will lead to a small value. Okay, so this first basis function computes the first component of my new feature vector, right? And the second basis function computes the second component of my new feature vector. So each data point now gets a new location in this new feature space. Okay, so let's see how this works. So we have this cluster of points. All these points, they are close to this first Gaussian mean. They are close to mu1. So that means that they will have a large value obtained from the first basis function. So they will have a large phi1 component. So large means close to 1 because the distance is close to 0. This exponential is close to 1. So it will correspond to this particular set of points. Now if I focus on the red cluster, so all these points, they are very close to mu2, so they will have a large feature vector phi2 or large feature value phi2. So this actually corresponds to this set of points, right? So because phi2 is very close to 1, it's because all these points are close to mu2. And then finally we have this set of points. These set of points, they are very far away from mu1, so they will have a value close to 0. And the distance is large, so e to the power minus something large will bring it to 0. So we indeed see that the phi1 components of this cluster takes on small values. And if you compare it to the mu2 cluster, obviously these points are further away than the red points, so they will have a lower value in phi2. and they're about the same distance away. So this cluster is about the same distance away to this average as this cluster is. So they have about the same value for the feature value phi2. Okay, so each data point, each point x, gets mapped to a new point phi of x. This is the vector obtained by stacking these basis function values, and these were the points x. Okay, so now this is what we've been doing all along when we talked about working with basis functions. We have an input vector x, and we can transform it to a new vector space via these basis functions. And now we are going to perform classification in this new, a new vector space. And because of our clever choice of basis functions, in this particular case they were Gaussians, we were able to nicely separate the groups. And now this actually enables us to work with a linear classifier, with a linear decision boundary, simply by focusing on, well, primarily, essentially, this is feature value phi2. So this essentially tells us that all points for which the phi2 feature value is large, those belong to the red class. So in a way, maybe I could also build a classifier just based on this feature vector. But in the general case, well, you want to use different basis functions to come up with a nice decomposition of your input data. Okay, so this is a very clear advantage of basis functions, right? So with a proper choice of basis functions, we can turn this highly nonlinear classification problem in essentially a linear classification problem via these basis function transformations. But this already also exposes a limitation of basis functions, because now I know what the data looks like. I work with 2D data, I can visualize this, I can get an impression of how my data is distributed, and I can come up with clever choices for my basis functions. But what if you go to high dimensional data sets? Then it becomes very messy to make these kind of visualizations and come up with decent choices for the basis functions. Right, so let's just quickly go over some advantages and disadvantages of working with basis functions. Maybe first and foremost, these basis functions allow for building nonlinear models or nonlinear mappings from input variables to target variables through basis functions. And that's what we're doing here, right? My classifier in itself is linear, but I first pull my input vectors x through some nonlinear function mapping. Okay, so essentially the whole pipeline is nonlinear in that sense with respect to x, so that allows me to build very complex functions in the end. And once we've defined our basis functions, then the methods that we used to work with on the input spaces x, they equally apply well to these new feature values. And that leads actually to the fact that we can obtain closed form solutions for least squared problems, and that we still have can work with a tractable Bayesian treatment, where this tractable treatment basically means that we work with linear function mappings and such. And so once we've been through this nonlinear mapping, then everything else can be kept simple, essentially. Now, some possible limitation of this is that these basis functions, they are fixed, right? They're not learned, so I have to decide on them, I have to choose them, and once I make my decision, I keep them as they is. But ideally, maybe you also want to incorporate this as part of your modeling framework to also optimally select or actually learn these basis functions. Now, that is an issue which we're going to solve in one of the upcoming videos when we talk about neural networks or multi-layer perceptrons. Then we consider the modeling of these functions as part of the learning process itself. And another limitation is actually this curse of dimensionality, right? So if my dimensionality grows, well, first of all, it makes it very complicated for us to come up with choices for the basis functions. But also we want our basis functions to cover my entire space, right? Because we want every input point x to be mapped to some meaningful new feature value. So that means, especially if you go to higher dimensions, we have a larger and larger space to cover with basis functions. So that leads to a very rapid growth of the number of basis functions. Okay, that basically covers what we call the curse of dimensionality, which is also discussed in chapter 1 of the book of Bishop. Now, what we're going to do in the later videos, we're going to focus on this limitation that the basis functions are fixed, and we're going to actually learn this via multi-layer perceptrons. But before we get there, we will continue going over the three methods for classification. So discriminative methods, probabilistic generative modeling, and well, next up is probabilistic discriminative modeling using logistic regression. When we first moved to the topic of classification a couple of videos back, I said we're going to roughly adopt three strategies for classification. One was based on probabilistic generative models. We covered discriminant functions, and today we're going to talk about probabilistic discriminative models, specifically focusing on logistic regression. Now, we started this video series on classification off with going over the theory of decision making. And the theory essentially told us that if we know the joint probabilities, joint probability distribution that generated my data, so these data point pairs, input class pairs, if we know this distribution, then we know how to make our decisions. So what we then started off with first going over probabilistic generative models. And we call them generative because if we know this distribution, if we are able to model this distribution, then we can also draw new samples from this distribution or generate new data samples. And we performed our modeling by modeling the class conditional densities, so the probabilities of each data point x given my class ck, my kth class, in combination with the prior class probability distributions, because the product of these two distributions gives us this joint. But more importantly, in the classification setting, we're interested in the posterior distribution for my class given my observation x. And using the class conditional and the prior, we can use Bayes' rule to obtain these posterior class probabilities. And from the point of view of decision making, these posterior class probabilities is the one that that's the thing we're interested in, right? We want to assign a new data point to the class which really maximizes the posterior class probability. What we then did, we fully let go of this probabilistic setting and said, okay, let's just directly model discriminant functions that are able to assign a new data point to a corresponding target via a function which is parameterized by a set W. And we came actually to this point of directly modeling these discriminant functions by making the observation that if we model in the probabilistic generative setting my class conditionals with Gaussians, with the same covariance matrix, then I end up with linear decision boundaries and linear models that essentially describe my classification behavior. So why not directly model these linear functions? And we did so via generalized linear functions. Then we, in the setting of discriminant functions, we covered two methods. We covered linear classification models obtained via least squares regression. Well, there had some issues related to outliers, but we also considered the perceptron, which also led to a direct modeling of my decisions via discriminant functions. Okay, now the third class of classification strategies, which we haven't covered yet, are the class of probabilistic discriminative models. So this falls somewhere in between, the direct modeling of discriminant functions, where we do not rely on any probability theory at all, somewhere in between that and the probabilistic generative methods, where we really adopt a full parametric probabilistic viewpoint on things. But since in the end for classification we are primarily interested in these posterior class probabilities, that is the thing that we are going to directly model. So the modeling becomes much more simpler if we do just this. Okay, so that will be covered today, probabilistic generative modeling. Okay, so the setting is again, we are giving a data set of data points x with corresponding targets. And these targets correspond to now a binary class. So I can pick one out of two classes for each target. And what I'm now going to do, I'm going to formulate this classification problem directly using these basis functions. So we are given a set of useful basis functions that map these inputs x to some other feature vector of dimension m. Okay, so I'm going to create a new feature vector obtained from my input vector x, of which the first component is always the constant value 1, and that allows me to describe any linear model directly with this scalar product, right? And what I'm also going to use the following notation. Instead of writing phi of x every time, I'm just going to write phi. And then it should be understood that this phi still depends on my input x. Okay, but that simplifies the notation quite a bit. Okay, so what we'll now focus on is a class of probabilistic discriminative linear models. And with linear, I mean the following, that my posterior class probabilities are modeled via a combination of this linear mapping followed by some non-linear function, which we will call the activation function. Now we've seen this form before, where for example we use the logistic sigmoid, and this is just a linear mapping. Actually, we're going to use the logistic sigmoid again, and that will lead to logistic regression. Okay, so we're going to use generalized linear models, meaning that we have this linear component over here. So of course, my data x is already transformed in a nonlinear way via these basis functions, but once I've done that, I have a linear model as a function of w. And then I have this activation function, which turns this into a non-linear mapping. And a second note is that I'm modeling here probability distributions here. So this mapping actually should ensure that the output value, so after pulling this through f, should take on values between 0 and 1. Okay, and then we saw in the probabilistic generative setting that we could obtain these posterior distributions via the class conditionals and the priors, and we took ratios between them, and that essentially allowed us to formulate the posteriors using logistic sigmoids or softmax functions in the multiclass case. But we're focusing now on two classes, and then we obtained models of the following form, where actually this component was replaced via the log odds, right? So the log of the ratio between my joint probabilities. And what we're going to simplify this. So instead of these log odds, we're going to define our own function. So that's sort of a loose modeling aspect to it. We're just going to find some model over here. And that then generates a posterior class probability. Okay, so as nonlinear function, we're going to use the logistic sigmoid. All right, so we are going to say that models of this type are going to model my posterior for class 1, and we're talking probabilities here. So the probability for the other class is then given by 1 minus this probability, which is denoted with a y as a function of phi. So that equals 1 minus sigma w transpose phi. Okay, so we're going to use this notation y actually for our generalized linear model, like really as a function of my input phi, and it returns a value somewhere between 0 and 1 that can be interpreted as probabilities. Okay, and since we are now considering the two class case, I can model my targets with zeros and ones, right? So I can also model, instead of defining two separate probabilities, one for class 1 and one for class 2, I could also build this probability distribution for the parameter t, which can take on the values zeros and 1. So I'm not going to explicitly do something like, say, for class C is C1 or for class C is C2. I'm just going to insert this variable t directly because I can use it with a sort of selection mechanism as we've seen before. So we have this model which models the probability for class 1. So if t is 1, then this thing is active. And then we have 1 minus phi, y of phi. And this thing should be active whenever t is 0. And when t is 0, this thing is inactive. Okay, so with this binary coding with ones and zeros, I can directly define my posterior distribution for this random variable t, instead of making two separate definitions for class 1 and class 2. So I'm going to repeat this actually. So in the generative setting, we actually said that we're going to model the posterior class probabilities for class 1 given x via the logistic sigmoid, which takes as input the log of these ratios the class conditional for C1 times the prior for C1. So this is essentially the joint probability for X and C1, the ratio with the joint for X and C2. Right, so this was the generative setting where we were first modeling these class conditional distributions and the priors, and then we could obtain a posteriors via this logistic sigmoid. And it turns out that if we work with Gaussians, then this becomes a linear function of this particular form, but where the W's were essentially defined via my parameters of the Gaussian distributions, which I used over here. And as mentioned before, now our focus is to just directly model these linear decision boundaries without first modeling these class conditionals and priors. So that simplifies our modeling approach quite a bit. And as we will see, and that's this slide, this actually leads to the fact that I'm going to use less parameters also in my model. So also in that sense, it makes it more simple, right? Because in this probabilistic generative setting, I said I'm going to model my class conditional via Gaussians and a class prior. Now focusing on these Gaussians, how many parameters would I need? For example, if my data consists of vectors which are m-dimensional. Now if my vectors are m-dimensional, then these class conditional densities are m-dimensional multivariate Gaussian distribution. So each mu parameter for each class. So let's just consider the per class case. So for one class, I need, for each of these means, I need m parameters. But then I also have these covariance matrices, right? And how many elements do these covariance matrices have? These have m squared elements. So in that sense, I would need m squared parameters, though this is not fully the case because these matrices are symmetric. So I do not need to define m squared unique parameters, but at least it scales with m quadratically. So here we have the number of parameters that scales quadratically with m, right? So if m becomes large, then also my number of parameters becomes large quite quickly. Whereas in my logistic regression case, I'm just modeling directly these W's, so that only requires me to have m parameters. So for my weight vector, I need m parameters, so that means this scales linearly with my number of basis functions. Right, so this is a very strong case. If I'm just interested in classification, then it makes more sense to do direct modeling of these posterior distributions, because then, well, I need way less parameters essentially. Okay, so that's what we're going to do. We're going to directly model these posterior distributions via functions of this form. And this is called the logistic regression function because it takes as input this linear transformation of my feature vectors, and then I'm going to pull it through this logistic sigmoid. So that leads to what we call logistic regression. Okay, so I'm modeling my target via this posterior class distributions. So this also means I can define a likelihood function given my data. So basically I can test how well my probability distribution describes these input-output pairs. So let's do that. So we're again computing this likelihood function on all my data, and we again make the assumption that my data is IID, meaning that this factorizes in the product of all these individual likelihoods. So the likelihood essentially that my model, which is described via this set of weights W, describes this input-output relation, and the probability of so the product and the probability, this probability of a given target given my input xn was given by this selection mechanism. So the probability for class 1 times 1 minus the probability of class 1, where these y-ends were really my posterior probabilities, right? Which were in turn modeled via these sigmoids. So this generalized linear model based on the logistic sigmoid. Okay, and from here on I'm going to work with the short notation for the feature vector for the corresponding data point xn. And I think maybe in one of the previous videos I already made this notation. It simplifies things a lot. Okay, so because we were modeling my targets via probability distributions, via posterior distributions, we could define a likelihood, and now we're going to optimize the likelihood function. So the likelihood that my model parameters W describe this data set, and that would give me a maximum likelihood model for logistic regression. And yeah, we've done this plenty of times. Instead of maximizing the likelihood directly, we're going to maximize the log of the likelihood, or actually minimizing the negative log of the likelihood. So let's see what this thing looks like. So we have minus this product becomes a sum, so minus the sum over all my data points. Then we have again this these products over here, which also become a sum. So I have the product of the log of yn to the power tn, but these powers move up front using these logarithmic rules, plus 1 minus tn. So that's again this power, the logarithm of y minus yn. Okay, so when I'm minimizing the negative log likelihood, I'm minimizing this particular error function. And this particular error function is known as the cross entropy loss. And this terminology, so cross entropy, that actually has a information theoretical background. What we're actually doing here is we're measuring the distance between two distributions. We have a ground truth target distribution consisting of these ones and zeros, and I modeled a particular distribution via these yn. So essentially it's a cross entropy between my ground truth and my predictive distribution. But maybe for this course it isn't too important where this terminology comes from. We're just going to call this particular loss the cross entropy loss. And it consists of this a product of my ground truth probability, like really probability 1 for class 1, times whatever my prediction set. So ideally we also want this to be 1. And also on the other hand side we have the probability or the ground truth label for my negative class times whatever my model came up with. So the log of my model's prediction. Okay, so whenever we have minimized this thing with respect to W, we've obtained our maximum likelihood solution for my logistic regression function. A quick remark here, so this is of course a function of W, because these yns, they are still a function of W. I just use this short notation over here. But my sigmoid, which takes as input my linear model described by W, is labeled yn. So this is a function of W, which we are minimizing. And in contrast to what we've been able to do so far we've been able to rewrite such error functions in a quadratic form, which we can exactly minimize, for which you can find a closed form solution for the minimizer. For this problem, we cannot do this because my functions yn are a non-linear function of W. That's because the sigma is over here. Okay, so that's unfortunate, but it turns out that this error, this cross entropy error, is a convex function with respect to W. So that means there's only one optimal value, and if we're able to find this optimal value, then we found really the global optimum for W, so really the optimal solution. And the fact that this cross entropy function is convex is really nice, because then we can just apply methods such as stochastic gradient descent, which we've seen before, because it guarantees that, well, if we apply the stochastic gradient descent iterates, we move downhill this convex energy landscape and end up with our globally optimal solution. Okay, now for now I'm not going to show that it is actually convex. You can find details about it in Bishop 4.3.3, but essentially the proof is we have to compute the Hessian of this error function with respect to W and show that it is positive definite. And if this is the case, then I'm dealing with a convex function, and that means that I have only one global optimum. Actually, I will say something about it in one of the upcoming videos when I talk about a second order optimization algorithm to find this optimal solution for W. But now let's focus a bit of what this cross entropy loss looks like. So, okay, we have the cross-entry loss. For reference, I put it over here. So for one data sample, this is the loss, right? So actually there should be a bracket over here. So it's minus of this entire thing. So it consists of these components, right? So whenever Tn is 1, so I want to predict the value of Tn is 1, this is my loss. And whenever my target is 0, then I'm considering this other loss, but these were probabilities, right? So the probability for the other class is given by 1 minus probability for, well, the first class. Okay, so now let's just focus on the case where I want to predict the target T is 1. So I'm focusing on this particular term, and this y is my predicted probability for class 1. This is what this logarithm as a function of y looks like. So on the horizontal axis is my predicted probabilities, which takes on a value between 0 and 1. And we're now focusing on the target is 1. And we see that if my predicted probability is close to 0, I have a high error, so I have a high loss. So we really want to minimize, reduce this error. So we want to push y in this direction. And if I am already close to my target, so now my prediction for the end data point is close to 1, and we see that this loss function is very close to 0. Okay, so this is what my loss function looks like when I plot it against my predicted probabilities. But maybe it's more interesting to plot it as a function of the linear component, as a function of this linear model W phi. So my yn was sigma of W, like the logistic sigmoid of W phi. And so if I plotted this in terms of this linear function, then I get this error function. Now, why am I plotting it as a function of W phi? I'm doing that because we used this model in our least squares regression case, right? So in the least squares regression, let me write it down. The least squares regression for classification, I assumed the model y was W transpose phi, where I used a quadratic loss. My prediction y should be close to my target squared. So that's what we did in the least squared regression case, right? And then we could also come up with linear decision boundaries, but we saw that we have actually that outliers were penalized a lot, even though this was completely unnecessary. And that was due to the fact that this loss function was minimized around the value 1, because we have this quadratic penalty that is minimized whenever my predictions are close to 1. So that essentially says if this linear part is highly negative, well, then I have a strong penalty, that's good. But also if it's highly on the positive side of this thing, then I also push it back to this 1. Now, if you compare this to the logistic loss, so now I'm looking for the case, so I'm predicting here the target T is 1, that's what I'm aiming for. Then I'm focusing on this model, right? So this is for T is 1, I have to focus on this component. So then you see if I'm far away on, let's say this is my optimal decision boundary defined by W. If I have points on this side, so highly negative, whereas actually I was supposed to be on this side, I have this penalty. So this looks a bit like a linear penalty whenever, so let me write it down. So this is like a linear penalty whenever my point is mapped to the wrong side of my decision boundary. But you also see if now I'm fully on the right side of my decision boundary, let's say green is my decision boundary, so that means I'm very much on this side, then I hardly penalize anything. So that is a good thing. So we see that this logistic regression does not suffer from this problem of outliers, which we saw in the least squares regression case. So we see that the penalty is close to 0 when my input vector is mapped to the correct side of the decision boundary. Then we see that my penalty only assigns a very small value, a small penalty to it. And it also said if it's not too far away from the decision boundary, then I still assign some penalty, meaning that I'm going to push it a little bit further away from this decision boundary. Okay, so we just saw that these type of points, they form no problem for logistic regression. Okay, so this really tells us that when we're talking about classification, we want to work with logistic regression rather than least squares regression, where we essentially made this analysis via this linear part of our model, because in our logistic regression, I work with probabilities, which are obtained by this linear model, and this logistic sigmoid, which maps all these inputs to a probability between 0 and 1. But then if I make decisions, so my decision boundary is essentially given via this probability has to be larger than a half. Then I assign my data point to class 1, and if it's smaller than a half, then it's assigned to the other class. And this means that equivalently, it means that my linear model has to be larger than 0. So my decision boundary for my linear model lies at the value 0. Now, and that then tells us if my predictions are far away from the decision boundary. So that's how we could interpret these linear models. We saw that in the linear discriminant model video. So if my points are far away from a decision boundary on the correct side, so I'm somewhere over here, I assign a low penalty. But if I'm far away on the other side, on the negative side, then I have this large penalty. And if I'm right at the boundary, right at the decision boundary, I still have a penalty that pushes it more to the correct side of the boundary. Okay, so that's a bit of an analysis of how this loss function eventually leads to finding correct decision boundaries, even in the case of outliers. Okay, so this slide wraps it up. So we have classification with logistic regression. The setting is we have a data set of input-output pairs, where I'm considering the two class case. So I could label my output with the label 1 or 0. Before I do anything, I map it through a new feature vector. So each data point is mapped to a new data vector via basis functions. Then what I'm going to do is whenever I make a decision on the class, so when I'm doing classification, I'm basing my decisions on the posterior distribution for my class C1, given my observation X, and it was parameterized by a set of W's. So this posterior probability is parameterized via my generalized linear model with my weight parameters W and my nonlinear function, the logistic sigmoid. And then to obtain these optimal parameters W, I'm going to minimize the cross entropy loss. So essentially, I'm going to minimize the negative log likelihood. And we can do this via stochastic gradient descent, for example, because the function is convex. I'm guaranteed to obtain the globally optimal solution, a W star. And in one of the upcoming videos, I'm also going to consider a second method for finding this W in an even faster way than stochastic gradient descent. So this part is coming up in the next videos. But once we have obtained such an optimal W, the classification is very simple. So we have a new data point X, and we evaluate my logistic sigmoids with my obtained values for W. And whenever this obtained probability is larger than a half, I'm going to assign it to class 1. Or equivalently, if my point mapped through this linear function is bigger than 0, I'm going to assign it to class 1. Okay, so this simply means that my decision boundary, given my optimal set of parameters, is simply given by setting this linear function to 0. Okay, that summarizes logistic regression. Next up, I'm going to talk about how to minimize this cross-entropy loss. We just saw that logistic regression is a great choice as probabilistic discriminative model. And in contrast to regular least squares regression for classification, logistic regression properly deals with outliers. And with respect to full probabilistic generative models, logistic regression is much more parameter efficient. Okay, so logistic regression is great for classification. Now let's see how we can optimize such models. So let's quickly go over the logistic regression setting. So we have this data set of input-output pairs where I'm considering binary targets. So I'm considering a two-class classification problem, which means that I can code my targets with these binary labels, a 1 or a 0. And this 1 and a 0 coding allows me to select the proper model, right? So instead of specifying for each class separately a posterior probability distribution, so this would be for separately for class 1, the probability after observing my data. I can model the probability for each class in one function, meaning that if I'm interested in class 1, then my t is 1 and I select, well, indeed, the probability for class 1. And if t is 0, then this thing becomes 1. And I'm focusing on 1 minus this probability, so I'm focusing on the probability for my second class. Okay, so this thing over here really is my probability for a target t given my input x and my model parameters w. So these x and w together, they are mapped through a probability via this logistic sigmoid function. All right, so we have this probabilistic model for the posterior class probabilities, and that allows us to define this overall joint likelihood function for my entire data set. So the likelihood that this entire data set was modeled via such a model for the posterior class probabilities parameterized by a set of parameters w. And again, I'm using the notation here that this phi n is really the feature vector associated with the end data point. Okay, and then the popular strategy for obtaining my optimal parameters w was in this probabilistic setting via maximizing the log likelihood. And the log likelihood in this particular case is given via the cross entropy loss, or actually this is the negative log likelihood gives me the cross entropy loss. And now in this video I'm going to explain how we can minimize this cross entropy loss. Now, as mentioned before, this error function as a function of w is convex, though it does not have a closed form solution because it's non-linear with respect to w. So this makes the problem non-linear, and therefore I cannot find a closed form solution, but it is convex, and that is nice. So it means that I can find the globally optimal set of parameters w that really minimize this negative log likelihood via stochastic gradient descent. Okay, so that's what we're going to do. This is my overall loss, my total log likelihood given all my data points. And well, we can always apply gradient descent to go to the local or the global optimum in this case. But if my error splits in the sum of individual errors for each data point, then this makes it a great candidate to apply stochastic gradient descent, meaning that we walk downhill this error landscape simply by taking a step along the gradient direction obtained by only inspecting one data point. So this entire loss for one data point will be called the error associated with the end data point. So this is what my loss looks like, right? So the sum over all these individual errors. Then the gradient or the stochastic gradient descent algorithm says that I'm going to find my new weight parameter. So I start off with an initial set of weights and I'm going to update it by stepping into the negative gradient direction, because that brings me downhill, that brings me down this error landscape. And my gradient was defined as the derivative with respect to all these model parameters concatenated into a row vector. And that's why I have to apply a transpose over here, because my weights are coded as a column vector. And well, we use the convention that my gradient is a row vector, so I have to put a transpose over there. Okay, so I'm updating my weights by taking a step down the negative gradient direction with a step size eta, and I'll give a little bit more information about this eta in one of the final slides. Okay, but we have seen this recipe for stochastic gradient descent before, and it all relies on the computation of this gradient, or of this gradient over here. So let's see if we can analytically compute this gradient, and if we have that, then we can insert it here, and then we have our update rule, which we can iterate. Okay, so that's what we're going to do. We're going to now look at one of these components of the gradient, because if we know how to compute the gradient with respect to the jade parameter, we can do this for all these parameters. So let's focus on this for now. So I'm computing the derivative of my loss, and this loss, so I'm going to use the chain rule here. So the derivative with respect to yn times the derivative of yn to wj, right? Because my loss is a function of these yns, and these yns are in turn a function of the model parameters w, right? So each yn was given by the logistic sigmoid of my weights with phi n. So if I have to compute the derivative of my error to w, I can first compute the derivative of my error with respect to yn. That's what I'm doing here, and I'm multiplying it. So this is a chain rule of the derivative of yn with respect to wj. Okay, so let's focus on the derivative of e with respect to y. So that gives me the derivative of this thing. So the derivative of the log is 1 over the thing inside the log. So the derivative here would be minus tn over yn. So recall we had this minus sign over here. Minus, because this minus also applies for this term, 1 minus tn over the derivative of this log. That's 1 over yn times the derivative of the thing inside this log. So I'm again using the chain rule here, and the derivative of this thing with respect to yn is minus 1, so times minus 1. And of course this minus 1 cancels with this, or it turns this into a plus, so let me simplify it a little bit. Okay, so this entire thing then still times yn, the derivative of yn with respect to wj. Okay, great, so I already computed this part of my gradient, and now I still have to focus on the derivative of yn, so really my logistic sigmoid model with respect to wj. So this is what I'm going to focus on next. So now we're going to apply the chain rule to this logistic sigmoid. So first we compute the derivative of the logistic sigmoid with respect to its input times the derivative of my linear model, which is not too hard. And actually for the derivative of the logistic sigmoid, this is actually what I said a couple of videos back when I first introduced the logistic sigmoid. I said it had this very nice property that the derivative of the logistic sigmoid is again an expression in terms of this function itself. I promised this expression would come in handy, and well, here it is. We're going to use it. I think I also said we're going to use the chain rule a lot throughout this course. And well, again, that's what we're doing. We're continuously computing chain rules over here. Okay, so there it is. We compute the chain rule of this thing. So first, the derivative with sigma with respect to its input. So that gives me this expression. So let's just write it out. So sigma of my linear model times 1 minus sigma of this linear model times the derivative of my linear model, so phi n, to wj, because that's what we were computing, right? Recall that the sigma of my linear model was called yn. Okay, and then the derivative of my linear model with respect to wj, that isn't too hard to show that it's going to be the jade component of phi n, but let me just quickly write it out. So we have the derivative of my linear model with respect to wj is given by, well, the derivative to wj of the sum. So I'm just writing out the scalar product over here. So the sum over all these basis function components or feature vector components. So wi times the ith components of my nth data vector. And so I'm only observing this particular variable, so wj, whenever I equals j, right? So this then, the derivative of this entire sum is just phi n j. Because if I is unequal to j, in the eyes of this wj, this is just a constant, so the derivative of the constant is 0. So yeah, the derivative is phi of nj, so let me mark that. Let's insert this over here, and then we've computed the full derivative. So this is then, and let me write it in the form of theseyn's to simplify it a bit. Yn times phi nj, right? Because these sigmas were yn. Okay, so now remember why we were computing this thing. It was because we were computing the gradient, or the derivative of my error with respect to the jade weight, and then we already computed this part, and then we had to compute the derivative of my logistic sigmoid with respect to double j, and that's what we just did. So let's just insert it then over here. Okay, so this part was computed on the previous slide, and this is what we just computed. So now we're going to fill this in, so that gives me Tn over Yn times the derivative, which is given as follows. So that's Yn1 minus Yn times phi nj. And we already see that things are going to simplify because these Yns cancel out. Then plus what we see over here, so that's 1 minus Tn over 1 minus Yn times what we just computed. So that's Yn times 1 minus Yn phi nj. And also here we recognize that this particular term cancels with this over here. Okay, so let's write this out again. So we have Tn phi nj minus Tn Yn phi nj, and then the other term plus, let's see, Yn phi nj minus Tn phi nj. Okay, and then these terms also cancel out, and what we are left with is a very simple expression for the gradient, namely Yn minus Tn times phi nj. Okay, so that's really nice. We computed the derivative of the jade component of this error function, and it really simplifies to the error that I make on my prediction. So because this was my prediction and this is my target, so this is my error times the jade component of the basis factor of the feature factor associated with data point n. Okay, so this derivative is this very simple expression over here, and that's not entirely a coincidence. There's actually some nice background theory with it. Actually, it follows that if you work with generalized linear models that work with a particular type of activation functions called link functions, then it turns out that the derivative or the gradient with respect to error always takes this form. So I really encourage you to take a look at Bishop 4.3.6 that explains that if I take the derivative of my error with respect to my W parameters, I end up with this form. Because it's not just for logistic regression that if I take the gradient of my error that it takes this form. This particular form also shows up for different classes of models. And it has to do with the fact that if I choose my activation function equal to what we call a link function, then I obtain this particular result. Okay, so this particular node refers to a broader interpretation of why this gradient takes on this simple form. But now let's just focus on the specific logistic regression case. So this is what we did. We're going to apply stochastic gradient descent on this error function. And to do so, we split this total error function into a sum of these individual errors associated with each end data point. And then we simply apply gradient descent by computing the gradient for each data point. And we just obtained an expression for what this gradient looked like. So the jade component of this gradient was simply given in the following form via the error that I make multiplied with the jade component of my feature vector. So that means that the gradient, the transpose of the gradient, so my gradient itself is a row vector and the transpose of the gradient is a vector, is simply given by multiplying this error with my input feature vector. And that then leads to the very simple update rule that my new model parameter is given via my old model parameters minus Yn minus Tn, so this is the error, times my feature vector. And it's really beautiful to see how simple my update rule now is, right? It's just my old weight vector and I add, well, the error times my feature vector to it. And this reminds us of what we saw in the perceptron algorithm, right? In the perceptron algorithm we had a weight vector plus actually my target times my feature vector. But what we did there, we only applied this update whenever we had a misclassified point. And now we're essentially updating for every point weighted with the error that we make essentially on the prediction, right? Because this was a prediction. If my target is 1, I want this thing to be close to 1. It's never perfectly to 1. So this will become a negative value, which means I'm going to add a little bit of this vector itself. So it's sort of like a soft version of the perceptron algorithm in that sense. Okay, so what I indicated in red refers to the similarity with the perceptron algorithm, but this entire thing refers to the update rule of my logistic regression. Okay, so this slide summarizes the recipe for stochastic gradient descent for logistic regression. So we have this energy landscape, which isn't quadratic. I sort of draw it quadratically, but it is convex for sure. And that means we can apply gradient descent to it. And the gradient descent algorithm is as follows. So we select some initial weight, W, and we specify a particular learning rate. And what we then do is we simply walk downhill this arrow landscape with step sizes eta in the direction of the negative gradient. And the gradient is given as follows, so that really leads to a very simple update rule. And now there's some remark, so if eta is small enough, then I'm bound to converge to my global optimum value. So I'm bound to end up here at W star, so the globally optimal value. But if my step size eta is too large, what is happening is that I jump, let's say over here, my steps are too large, so I sort of keep skipping over the optimal value. So if eta is too large, then I may come close to my data point, but I will never reach this particular point. But if eta is too small, then it takes me a lot of time steps before I actually end up at my global optimum. Okay, so that's it. If I select my eta small enough, I'm bound to converge to my global optimum. So really the minimizer of my error landscape. And that gives me a globally optimal logistic regression model. Now what I'm going to do in the next video, I'm going to present an alternative to the stochastic gradient descent algorithm. I'm going to present a second order optimization method where a stochastic gradient descent is typically referred to as a first order optimization method because it is based on first order derivatives on the gradient. And in the next video we talk about a second order optimization method which converges faster to the global optimum, so with less iterations, and it also doesn't rely on picking a particular learning rate eta. In this video, I'm going to present a second order optimization scheme for finding logistic regression models. And this scheme will be called Newton-Raphson optimization. And along the way of deriving this second order optimization scheme, I will show that the logistic regression problem, the logistic regression error function, is actually a convex function, and hence it only has one globally optimal solution. Again, a quick recap. We have data pairs, input-output pairs, where the output is a binary target. So we're considering two-class classification, and we are going to base our prediction via a probabilistic discriminative model. So really we try to predict the probability of my data point belonging to a particular class, to class 1. And the probability of my data point belonging to class 1 is given by this logistic sigmoid function. Now, in order to obtain my optimal model parameters W, I'm going to minimize the negative log likelihood. And the negative log likelihood is given in the following form. And this thing over here is often called the cross entropy error function. Okay, and this cross-entry error function is a convex function with respect to W, which means that it only has one globally optimal solution, and we can find such a solution, for example, via stochastic gradient descent. And in this video, I'm going to present a second-order optimization algorithm to find our globally optimal parameters W. And along the way, I will show that this function is indeed convex by inspecting its second-order derivatives. Now the approach is as follows. So this Newton-Raphson iterative optimization scheme is in a way similar to stochastic gradient descent, mainly based on the fact that we have this iterative scheme where we start off with an initial guess and then we update my model parameters W at each step. And now we're essentially going to make a quadratic estimation of my error function, whereas previously we used a gradient, which essentially gives us a linear approximation of my function. And with that I mean the following. Suppose we have this convex error function, because my cross-entropy loss was convex, and I have an initial estimate for my parameters W, so this is W time step 0. What my gradient descent algorithm does, it looks for the gradient, so let's say it points in this direction, and then I'm going to walk downhill this gradient direction. So really what this gradient does, it gives us a local approximation of my function as a linear function. So it looks like this. The error, it says my error increases if I go in this direction and it decreases if I go in this direction. And of course we want to minimize the error, so we move along the negative gradient direction. But we have to pick a step size, right? Because it keeps going down forever because it's a linear model. So if I really want to minimize this linear approximation, I just go to infinity and I get my error, which is minus infinity, which doesn't make sense, of course. So I have to pick a certain step size. So that's what we do. And every time we estimate the gradient, pick a step size, and then we walk downhill until we reached our optimal value. Okay, so with stochastic gradient descent, I have to work with a particular step size, eta. Now what we're going to do in this second order approximation scheme, I have these blue lines correspond to my true error function. And now I'm going to approximate locally, so I'm considering my function around the weight set W0. And I'm going to make a quadratic approximation of my error function around this data point. And maybe it looks something like this. So I make this quadratic approximation, so E tilde is a function of W, and it maybe looks something like this. And what I'm then going to say, my next model parameters are going to be given by the minimizer of this approximation. So it's a quadratic approximation, so it has one global minimum. It lies, for example, at this particular point. So that will be my next model parameters at time step at tau plus 1. Okay, so I'm going to repeat this. I again obtain this quadratic approximation, and my approximation says that the global minimum of my approximation lies somewhere over here. So, okay, that gives me the next point, and so on. And by doing this, by making this quadratic approximation, I actually take curvature of my energy error landscape into account. I sort of know from local inspection that I have to steer a bit in this direction and make my step in this corresponding direction. And that in the end leads to the fact that not only I reach my global optimum of my error landscape in less steps, it also shows that I do not have to select a particular step size. Because in my linear approximation, I really do have to set a step size, otherwise I keep on going forever in one particular direction. But in the quadratic approximation case, my approximation says there is one minimal value of my approximative error landscape. Let's just pick that value. So there's no reason to set or select a particular step size. Okay, now in this video I'm going to explain how to obtain such a quadratic approximation, which essentially is done by a Taylor expansion. Then I'll show how to minimize this approximation, and that gives me the next weight vector. And at some points, these points, they lie very close to each other because I've reached the global optimum. So basically I stop whenever my new iterate is very close to what I already had. Okay, so this gives me an algorithm for walking downhill this error landscape, taking the curvature of my energy landscape into account. And in the end, I will converge to my globally optimal value for W. Okay, so what does all of this look like? I said I'm going to approximate my error function W with a second order Taylor expansion around the weights that I'm currently considering. So I'm computing a second order Taylor expansion around W at time step tau minus 1. Now, what does such a Taylor expansion for multivariate functions look like? So it's just a Taylor expansion as we've used to. So we take the function value at the point that we're considering, plus the first order derivative, which is now the gradient, times a particular step size relative to this central point, plus my second order derivative, which is captured via this Hessian matrix, times, well, my step size squared. And in the multivariate case, that means I multiply it on the left and right. So this Hessian is multiplied on the left and right of this with this step size. Okay, so this is what the Taylor expansion looks like. It's an approximation. It's a second order approximation of my error function W, where I'm approximated in the following. So I center this approximation around my current estimate for W, and this is then a relative offset parameter. And this Taylor expansion requires to compute first order derivatives, first order multivariate derivatives. So it requires us to compute the gradient, which we've done already in the previous video, but it also requires us to compute the second order derivatives, which are captured in this Hessian. And this Hessian is a matrix with rows I and columns j given by my second order derivatives of my error Wi, Wj. And this Hessian matrix is symmetric. It is symmetric because I can change the order here. The derivatives in this vector space commute, basically. So I am allowed to change this order, and that tells me that the Hessian is symmetric. For now, let's just focus on the recipe. So now I want to make my update rule using a optimal step in the right direction. And I'm going to pick the step delta W that minimizes my approximated error function. So that means, so that's what I've explained over here, right? I made an estimate of my error functions. Those are those green contours. And I take as next data points the W that minimize this, this approximate error landscape. Okay, and now my approximation, so this E tilde is a quadratic function of this step size delta W, right? So you have a linear component and a quadratic component. And so it means it has one globally optimal step size. And we will find this by taking the derivative with respect to my step size and setting it to 0. That's what we've been doing so far in any of these optimization problems, right? So we take the derivative and set it to 0, solve it, and that will give us my optimal value. And now we're going to do the same for this approximated error function. So that means, okay, we're going to compute the derivative with respect to delta W. So the derivative with respect to delta W of this term, so not to W, but to my step size. So this is the parameter in this approximation. Okay, so we compute the derivative. That will give me the gradient itself. Then we take the derivative of this quadratic term. We see delta W over here. So this one drops out and we multiply this with a 2. We've seen this actually before, that the derivative of such a quadratic function would be 2 times a half times, well, what we had, transpose Hessian. And of course this factor cancels out, so let me just remove it. Okay, so this is the derivative with respect to the step size delta W, and we set it to 0. And this is my optimality criterion, right? So this is what we're going to solve now for my step size delta W. Okay, let's solve this. So we move the gradient to the other side and then take the transpose on both sides. So this is minus the gradient transpose. Right, I moved this to the other side and then took the transpose of both sides. And since the Hessian is symmetric, this transpose doesn't do anything. And then we see that we find the optimal solution for the step size to be minus Hessian inverse gradient. Okay, now let's do a dimensionality check, or let's see what we're dealing with here. So in our convention, the gradient is a row vector. So taking the transpose turns this into a vector. So matrix vector multiplication gives me a new vector. So my new update step is again a vector. So that's correct because W is a vector. And now we take a direction in this step. So we have our previous weight vector and we add now this step to it, which is given by minus Hessian inverse times the gradient transpose of my error. Okay, so let me quickly get back to this figure. So we were analyzing, making an approximation of my error function around my initial W. That gives me this, for example, this quadratic form over here, which is given by this Taylor expansion, this Taylor approximation. And then we solve basically for the minimal value of this error function. That gives me the next, that actually gives me a delta W relative to this initial W naught. So we jump in that direction and that gives me the next weight. So that's what you see over here. This is the update rule. Okay, so we see that, well, first of all, we do not need to define a step size because we immediately jump to the next optimal location given our approximation. So, and what we need to compute then is the gradient. Well, we've done that so far. I'll go over that in a minute. And we have to compute the Hessian, and that's also what I'm going to show next. As for the gradient, we showed that in the previous lecture for, if I say my error, if I say that my, let me write it here, if my total error of W is given by the sum over all its components, so that's denoted with this En. Okay, this is my error, and this is the gradient vector, so we took the transpose here, of my error, of my individual error for this data point. So that was just the error that I make for that data point times the vector. So for the full gradient, it looks like this. So the sum over all data points of yn minus tn phi n. So, and we can write this in matrix vector notation as follows. So we have this design matrix containing all these feature vectors times my prediction vector. So stacking all my predictions in one vector minus the target vector. Because recall that the data matrix or the design matrix is of size n by m. So for each data point I had a feature vector and I stack them on top of each other. So I have all these rows of data points. And then if I take the transpose, that means I'm summing and multiplying over the n axis of the data axis. So I'm multiplying all these errors with the corresponding basis functions. And that will give me a vector of length m. Okay, so we compute the gradient in one step via this matrix vector multiplication. Now also the Hessian, we can write it in this matrix vector form by writing out the ith and jth components of this matrix. Now we already computed the gradient with respect to the jth component. That looks like this difference vector times the jth component of well, the nth data point, the nth feature vector. So this thing over here is essentially the dwj of my error function. And now I'm computing the I derivative of this thing. And remember, we're computing derivative with respect to w, and the w is hidden in this yn, right? Because each yn, let me write it over here, each yn is given by the logistic sigmoid of my w vector transpose phi n. Okay, so let's compute the derivative with respect to w of this thing. This thing doesn't depend on w, so I have to focus on the product of yn times phi j. So that gives me the sum, n is 1, the sum remains there, phi j of data point xn, and then the thing that actually depends on w, so the dyn dwi. Okay, so this thing is what I have to compute. And it's also this thing of which we already computed the derivative previously. So let me write it above. The derivative of this thing is yn times 1 minus yn phi I xn. Okay, so let me insert that. That gives me the sum from n is 1 to n of yn 1 minus yn phi I phi j. Okay, so the ijth component of the Hessian is given by this expression. Now let's also write this in matrix vector notation. So that gives me, so let's start off with this. So this was my expression for the Hessian. So yn phi n transpose. And I can write it like this because the Hessian is an m by m matrix, where for each I and each j I have m components. So essentially I'm multiplying, making this multiplication for every ij, and I can do this by taking the product of my vector n with its transpose. So that's essentially this thing describes this for every ij. Okay, so this gives me the Hessian matrix. Let me see if I can also reduce this sum over n. So we can do that by working again with this design matrix, transpose some diagonal matrix. Okay, so what is happening here? Each design matrix is again a dimension n by m. So this will be, with the transpose, this will give me a matrix of m by n. So I sum over the n axis also for this case, where since this is going to be now a diagonal matrix for which the Rn, so the diagonal is given by yn 1 minus yn, and the off-diagonal components are set to 0, so meaning if n unequals m. Okay, so now we also have an expression for the Hessian in this matrix notation. Okay, so please verify yourself that this is indeed the case, right? That I can use these design matrices with a diagonal matrix R, which essentially encodes these weights or these components of n. Okay, so we have just derived the gradient and the Hessian given the things that were provided to us, right? We have this data set, which we use the basis functions to create new feature vectors for each data point. So that's all encoded in this data matrix. And these are my predictions and these are my targets. And with that I can compute the gradient and I can also compute the Hessian. Now that we have actually computed the Hessian, we can show that indeed the arrow function is convex. Where we say that a function is convex whenever its Hessian is positive definite. And positive definite basically means that if I multiply this Hessian on the left and right side with some non-zero w, then it always returns some positive value. So if we can show that this is the case, then we have proven that our Hessian is positive definite and indeed our cross entropy loss is convex. So let's quickly do that. So we have computed our Hessian as follows, right? Using these design matrices, which were of size n by m. So we have n data points and m feature vectors. And then we have this diagonal matrix, so a sort of weight matrix, which is of size n by n, which for each data point assigns the following weight. So the product of these two probabilities. Okay, so what I'm going to show next is that for every w transpose Hessian w, that this returns some positive value. So let me just write this out. So it's if w transpose times my design matrix transpose times r times phi times w. And what I'm going to do next is make use of the fact that each of these yn's they're either bigger than 0 and smaller than 1, meaning that I can take the square root of these diagonal elements. So actually this allows me to write R as the product of these two square roots, where I'm defining the square root of my matrix R as the diagonal matrix given by the square root of yn times 1 minus yn. Okay, I can do this, right? So this expression can be rewritten as W transpose my design matrix transpose square root of R phi W. And what we're essentially seeing here is we essentially take the scalar product between two vectors. So let me make that a little bit more explicit. So we're actually computing the product of this vector. So this is a matrix. This is a matrix times a vector gives me some new vector, and I take the transpose of this and I multiply it with itself. So that's essentially what is written over here. And the scalar product of a vector with itself boils down to taking the norm of this vector squared. So what we see is that we can rewrite W transpose Hessian W in the following form. And well, a norm always gives me a positive value, or it gives me 0 when the vector is 0, but we're considering all non-zero W's. So this proves that for every non-zero W, my expression returns some positive number. So my Hessian is indeed convex, so it satisfies this criterion for all non-zero vector W's. That's what we've shown over here. So indeed, my Hessian is positive definite, and this means that my error function, my cross entropy loss, is indeed convex. Okay, and then we have everything in place to compute this update rule, where we have to compute the gradient, which we can do as follows, where we have to compute the Hessian, or actually the inverse of the Hessian. So this is actually a computationally expensive step, but we can do this. And for the Hessian, we make use of this sort of diagonal weight matrix, where we weight this inner product between all these vectors using the weights yn, 1 minus yn. And this followed from, the computation of the second order derivatives. Okay, and now with this in place, we can actually rewrite this update step to a particular form, which actually led to the fact that people started calling this the iterative reweighted least squares algorithm, because each update step can actually be formulated as a least squares problem, where the new weights are obtained via some equivalent fitting least squares problem. And I'm going to show this as follows. So what I'm going to do, I'm going to rewrite this expression into a form that corresponds to the solution to a weighted least squares problem. And I'm going to start off by factorizing this thing. So I move this thing up front. Okay, let me just write it out. Okay, you can see that this is still the same, right? So this Hessian, so this is actually the Hessian inverse. If I now multiply with this, I end up with W tau minus 1. And if I multiply with this thing, I obtain this form over here. So I'm just rewriting things now, because especially in the next step, it will start to become clear what I'm doing. So let me also just write that one out. Now, what I did here, I introduced this new variable, z or z, such that I could write it in this form. So it's a lot of trickery going on here, but I'm doing this because this term over here can then be cancelled out, because we have this r times r inverse, actually this phi times r inverse times this thing. So this entire thing then can be get rid of, and that would give me that this update rule is given in the following form. So this was the Hessian inverse as we saw it, R Z. Okay, and this is what we wanted to see. We have that my new weights at times at tau are given as follows. And just looking at this particular form, it resembles a lot the least squares solution, right? We've seen this before, but then without the R. So if this R wouldn't be there, it would be just a least squares solution to some fitting problem. But now we introduce these R's, so these R's are additional weights, and we have this Z, and that's sort of the thing that we want to predict. So what kind of regression problem would this correspond to? I'm going to write that out over here. So this would actually be the solution to the following minimization problem. So we're looking for the weights W that minimizes a weighted least squares, where we have W transpose phi n minus Zn, where this would be the target in my fitting problem, and these are like additional weights that sort of weights the importance of, well, the data points that I'm considering. So not to be confused with my parameters W, right? These are just weights used to weigh the error basically that you're making. Okay, now that's the reason why people call this the iterative reweighted least squares algorithm, because in every update step I'm essentially solving a weighted least squares problem where my weights are given by these weights which were also used in the Hessian computation, basically the product of my probability for class 1 times the product times the probability for my other class, you know, a 1 minus the probability for class 1. And my targets are given as follows. And to be honest, I cannot give a clear interpretation to this, but the point is, in each step we solve this weighted least squares problem, where at each step we have to update the weights because these weights depend on W, on my current solution W, and I update my targets. Okay, so the main point of this slide was to show where does this iteratively reweighted least squares name come from. So that this actually means that if we now draw this, so green here shows the path obtained via stochastic gradient descent. So if we have curvature in our energy landscape, we sort of take a roundabout route because we just walk downhill without considering like the overall landscape. Whereas in my second order optimization scheme, so the Newton-Raphson scheme, I actually take the curvature of my error landscape into account, and that allows me to come up with a shorter route. And the idea behind this Newton-Raphson optimization was that we make an approximation of our error function, like a quadratic approximation, solve it for its optimal location, and jump to that point. Then again, we make this quadratic approximation and immediately jump to that point, where we start off with an initial set of weights and the weights at the next time step, where in each step the new model parameters are obtained via this weighted least squares problem, where at each time step you solve this weighted least squares problem with targets that are updated based on the current set of parameters, and also my weights for this weighted least squares are updated based on my current predictions. Okay, now there's some clear advantages of Newton-Raphson over a stochastic gradient descent. First of all, we have that there's no need to define a step size. So that's nice. It doesn't depend on, well, this additional hyperparameter, the step size. It also converges faster. So faster convergence than stochastic gradient descent, but it requires the Hessian. But most importantly, we need to compute the inverse of the Hessian. And this is computationally the most expensive step of this update scheme, computing the inverse of the Hessian, because computing the inverse of a matrix often scales cubically with the number of elements in the Hessian, with the number of basis functions that are considered. So it scales with m to the power 3. And there's a lot of research going on figuring out which kind of matrices can be inverted quickly, and also how to make maybe clever approximations to this. Because it is nice that you can obtain your final globally optimal solution with less steps. It's just that these steps are hard to compute, and there are smart approximations and alternatives to this actually. Okay, so what I described was an alternative for stochastic gradient descent, a second order optimization method. And at this point, I just want to point out that such second order optimization methods do not just apply to the logistic regression case, but it could be applied to other type of optimization problems as well. In the next couple of videos, I'll be talking about artificial neural networks, also known under the name multi-layer perceptrons. We'll start off by interpreting neural networks as functions that compute feature vectors, which are subsequently used for classification or for regression. Now, recall that so far we have computed feature vectors from our inputs via fixed basis functions. In the next videos, I'll show that we can actually learn such basis functions via neural networks. Now, in this video, I'll first explain what neural networks are and how they relate to these basis functions. And then in the next video, we'll go over some examples in the context of function approximation. Now let's start by recalling how we were dealing with basis functions so far. So the setting was always we are provided with some data set and targets, and then we want to solve some problem with it. And our data points were always considered to be vectors in some d-dimensional vector space. And then what we often did was we first computed feature vectors given my input. So my inputs were transformed to a new space using basis functions, and we can use the basis functions such that eventually a regression or classification problem becomes easier. And so far we really picked these basis functions ourselves. Just by inspecting the data, we thought that maybe Gaussian Bayesian functions or maybe polynomials of a certain order would be useful to solve a problem with. Okay, another thing is we typically use set the zeroed basis function to 1, because that allows us to incorporate the bias in our models by just considering functions of the form, so linear functions in a regression case, for example, just taking the scalar product of my basis functions or my basis feature vectors with a set of weights. So then I obtain a linear model, a linear function of W, but it's a nonlinear mapping because I first pull this X through my basis functions. Okay, and then for linear regression, we were working with targets that could take on any value on the real line. So it was a continuous fitting problem. So we do not work with any activation function. We just work with this linear model. Now in the classification setting, our targets took on binary values. So they could either be 0 or 1. So we had to work with a nonlinear activation function that basically ensures that we have this property. And then we can come up with proper classification frameworks and optimization schemes. For example, for binary targets, an optimal approach was proven to be logistic regression, in which case we still have this linear component over here. So that actually leads to linear decision boundaries in the end. But we have this nonlinear function over here. So this nonlinear activation function. So for classification, we considered so far generalized linear models. So a linear component, linear in W, but overall nonlinear because we have this activation function. Okay, so that's what we've seen so far. And I also said that maybe we also want to learn the basis functions ourselves, because now we're hand designing them. We made choices there, and for low dimensional cases, we could still do it, but for higher dimensional cases, it's very hard to come up with a proper choice for basis functions. So ideally, we want to make this part of the learning procedure. And that's precisely what we're going to do when we optimize neural networks. Okay, now let me remind us again that for convenience, we will work with feature vectors which have like a constant 1 as the first component, and then the original data points, the original vector. So we prepend our data vectors with a 1 such that we can include the bias the bias parameter inside the set of weights that we're going to consider. Okay, and now we take on the viewpoint on neural networks as functions that work with adaptive basis functions to compute the feature vectors. So these feature vectors are then later used for regression or for classification. But the learning of this basis function will be part of the learning process itself. And these particular basis functions will be parameterized via generalized linear models. And this means that each basis function takes on the following form, right? So the basis function is a function of x, and it is parameterized by its own set of parameters w. And so this basis function is defined in the following way. So it's this linear mapping followed by some nonlinear activation function. So this part is just a linear model, and this part is a nonlinear function mapping, nonlinear, what we call an activation function. So to make this a little bit more explicit, our linear part really consists of taking a linear combination of my input values weighted with the corresponding weight values, and these w's, those are parameters that now become part of the learning procedure. And once we've linearly transformed our inputs, we pull it through this activation function. So we see that each basis function is now defined by some generalized linear model. Okay, and now we have defined our basis functions, which are parameterized by a set of weights w, which we are now also going to learn. Okay, but now we have these basis functions and we want to solve problems with it. And we're doing this just like we've been doing so far. So for the regression case, we just work with a linear model. So a linear model applied to my feature vectors. And these are my now computed feature vectors. And I'm going to take linear combinations of this to make a prediction for y. So let me write this out. So this looks like my linear model, the scalar product with my new feature vector. My new feature vector, I can write it in this way, W1 transpose X. And you see I'm now indexing the set of weights, right? Because this set of parameters is associated with my first step of transformation, so used in my basis functions. And then the second set of weights is used in my output layer, that these contribute to my final output prediction. And what I did over here, I defined this matrix, so this a big W1 to be, the collection of all my basis function vectors, right? So if I put them all next to each other, so let me do that. So each basis function had its own set of linear parameters w, and if I put them next to each other, then I can obtain the predictions or the feature values for each m in one go via this matrix vector multiplication, where each time I multiply the weights of basis function 1 with my input, and then of 2 with my input, and that gives me this column vector of new feature values, which are then pulled through this activation function. So this thing over here is what we've been used to seeing like this. So a vector of feature values obtained from some basis function, but now the basis function is learned. And then we obtain our regression model as a linear model. So this scalar product of my model parameters w with this learned basis function. So really a regression problem can be formulated as a two-layer neural network in that sense. So we have a first layer that computes the feature vectors, and then we have a final layer that contributes to my prediction. Now, similarly, we can use these learned basis functions to solve classification problems. And in that setting, we work with generalized linear models, but now it's a generalized linear model using my learned feature vectors. So my feature vectors were obtained via this weight matrix 1 with my feature vector x. Where again, in this matrix vector multiplication, I multiply the set of weights for each basis function with the input, the next basis function for this input, and then pull it through this activation function. So again, this thing over here gives me my learned feature vector. And then in a classification setting, we use as activation function, we use the logistic sigmoid, or in the multi-class classification case, we worked with a softmax function to turn these values into probabilities. Okay, so what I just showed essentially defines two-layer neural networks. And in the upcoming slides, I'll show some examples of deeper neural networks. But these are just two-layer neural networks, and we gave them the interpretation of basically working with learned basis vectors, basis functions. Okay, so that defines a two-layer neural network, and as a model, as a mathematical model is given as follows. But we are also going to get used to these network diagrams. This is what you typically see when people explain how they design the neural networks to others. They work with these kind of visualizations because those are often more easier to interpret than these equations. And I'll show some example later on where this definitely is the case. So let's go over the components of multi-layer perceptrons, of neural networks. So first of all, we have the input units. So we have an input vector x, which is prepended with a 1. So we have x1 up to xd. And each of these components is called an input unit. So each such value is represented with one of such dots over here. So I have a d plus 1 dimensional input because I prepended a 1. And then each input unit is represented as one dot. So this dot, you should really think of it as taking on just one real number, right? It's one of these components within my vector. Then we have what we call activations, denoted with A, and they're also indexed with some index M in this case. So this A is a vector of activation, so A1 up to AM. And this vector is obtained via this matrix vector multiplication, right? My first model parameter is W times X. And this gives me an m-dimensional feature vector, though it's not yet the final feature vector because this is just a linear part, and we first have to pull it through this nonlinear activation function to turn this into what we refer to as the basis function feature vectors so far. Okay, but before we get there, we do this linear mapping, and this leads to what we call the activations. So let's draw that over here in yellow. Then we have what we call hidden units, denoted with Z and also with the same index M, because these ZMs, those are the feature vectors obtained from the activations by really activating them with the corresponding activation function. Okay, so we have all these hidden units, Zm, and they're obtained by applying this activation function, so by applying the activation function H to A, and that gives me the corresponding hidden unit. And these hidden units will in turn be used as inputs for the next layer, right? So these hidden units are the feature vectors at that point used to, well, obtain my new feature values using this linear combination of the hidden units. But we're considering here the two-layer neural network, so my next layer would be then my output layer, and the units or the values at the output are called the output units, and these output units are typically denoted with Y with a particular index kth. So this is the kth output unit. And these output units, as said before, form this vector of outputs y1 to yk, and these are obtained with my second linear mapping, with my second set of weights from my hidden units. And this would then give me my k-dimensional output vector. Okay, so each value in this output vector corresponds to one of such nodes, and it's called an output unit. So this would be my kth output value. It's just a number, it's just a real number. So this is just a reminder, at each node we should think that we place some real value, right? And we call each of these values, we call them, well, units. So we have an input unit x, we have a hidden unit zm, and we have an output unit yk. And then finally we work with these activation units. So each layer has its own activation unit, but typically we just say we use one unit throughout my network, except maybe for the output where we maybe make specific choices that depend on the problem, right? In linear regression, maybe you do not want to have any output activation, but for logistic regression or for classification, you maybe want to apply a logistic sigmoid or a softmax to the output layer. But generally we say we stick with one choice for activation function that turns my activations into the hidden units. Okay, so these are all the components of a multi-layer perceptron, of a 2-layer neural network in this particular case. Now it's only 2 layers. So we start off with an input unit. So that's all those input values, xd. Those are transformed linearly via my weights in the first layer to give me the activations, of the first layer. And these activations are in turn turned into hidden units, the ZMs, by applying this activation function h to my activations, and then those hidden units are used as inputs for the next linear model. So that's why we apply this W now here. That gives me all these output units, and then we can decide to apply another activation units to my an activation to my outputs. So we have inputs x, we have this matrix vector multiplication with my first set of weights, W1. That gives me, in the end, the activations, and then it gives me the hidden unit, so this hidden unit vector set, which is then transformed via linear transformation with my set of parameters W2, and that gives me my output activations. Okay, so that explains all the components. Now let's just take a quick look at choices that we have for the activation functions. What is listed here are some popular choices for activation functions. The logistic sigmoid, that's classically one that is used a lot in neural networks. We, for now, used it only for the output layers to turn a problem into a logistic regression problem or a classification problem. We already saw this logistic sigmoid before. So this is the logistic sigmoid. And it's drawn over here as this green line, right? So it squashes all the values of my linear model to the range 0, 1. And that allows us to interpret things as probabilities, essentially. Then what we see in red is the hyperbolic tangent. So the hyperbolic tangent, which is given by e to the power x minus e to the power minus x divided by e to the power x plus e to the power minus x. Okay, that's indicated here in red. It also has this nice squashing property, but now it squashes all the values between the values -1 and +1, and it has this sort of linear part over here. So close to 0, this function is linear, but if my activations take on very high values, then those get truncated at the value 1, essentially. So those two are classically quite popular choices, but it turned out that if you go deeper into your networks, then these activation functions aren't actually so nice to work with. And this has to do with the fact that when we optimize these models, we have to compute gradients. That is what we have seen also in the other models. We apply gradient descent type of methods and apply chain rules. And now if you pull strings to such activation functions, then you also need the derivative of these kind of things. And you see that both the logistic sigmoid and the hyperbolic tangent, they sort of flatten off to some constant value. That also means that the derivatives at these locations will take on very small values. And this leads to numerical instability in the end. And when we optimize neural networks with such activation functions. And the type of activation function that doesn't suffer from this is the rectified linear unit, or ReLU. And that is given by the max of 0 with A. So this function really is a linear model of A. So it has this linear part, and everything below 0 is just mapped to the value 0. So it's like a threshold function. So this rectified linear unit that ReLU is by far the most popular activation function at the moment out there. And then I have a small but very important remark about working with activation functions. Because maybe you're tempted to think, okay, why do we need activation functions? Things become much more simpler if we don't apply them. And the main reason actually is that it doesn't make sense if you build deep neural networks or neural networks without activation functions. Because if you do not apply an activation here, then I just concatenate linear operations one after each other. And a concatenation of linear operators in the end result in one netto linear operator. So then you assign all these weights, and in the end you could have done this directly with one linear model. So in order to make things complex and interesting, we do need activation functions, otherwise we just end up with some linear model. Okay, so let me just write that down over here such that we don't forget it. We need activation Okay, so don't forget about this. We do need activation functions, otherwise we're just learning linear models, and then we don't need all this complicated structure over here. Now let's familiarize ourselves a bit further with neural networks by considering types of neural networks that we actually already saw throughout this course. First of all, we already worked with one-layer neural networks. So these are just linear models, right? Or maybe generalized linear models. And we work with them in the linear regression case. So really what we did in the linear regression case, we said, okay, we want to predict our outputs or maybe the target means of my target distributions with a parameterization vector W, just via this linear mapping from input to output Y. So that's essentially what you see over here. All the input units are multiplied with the corresponding weights, and that gives me my output Y. And in the regression case, we wanted to regress any value on the real line, so we do not apply any activation function, or in this case, the activation function is just the identity operator. Okay, so we already encountered one-layer neural networks. We also encountered them in the classification case, where we were building classification models for each class K. We wanted to predict some probability, and this probability was given by such a generalized linear model. So again, a linear combination of the input. So each kth output, each kth class had its own set of weights, a W. And when dealing with K classes, we applied the softmax activation functions to these activations, such that these outputs could be interpreted as the probability for class K given my input X. So that looks like this, right? So each output prediction YK was obtained via a linear combination of my inputs, and then we applied a softmax activation function to all these output predictions. So that describes a linear classification model with K classes as a one-layer neural network. So those are just one-layer neural networks. That's not super interesting, right? It's just regression or just classification via generalized linear models. So things become interesting when we go deeper. And what this essentially means is that we have all these mappings, so a linear transformation followed via a nonlinear activation function that gives me a new feature vector. Again, linear combination, activation function. So we apply all these mappings, and you could think of it as in the end ending up with a very complex basis function as a function of X, right? This value is obtained via all these mappings, so it's a function of X in the end, where this basis function is then essentially parameterized by all the weights before this. And then once we have obtained such a feature vector, then these values can be used to make our final predictions to solve the problem that we were actually dealing with. And so this could be a multi-target regression problem, or it could be a multi-class classification problem, or whatever the problem is that you're working on. Right, so we can build very deep neural networks, where deep means really how many layers you have. So a deeper network has a lot of layers. So we can essentially now build very deep networks to come up with very intricate, very complicated feature vectors at this point. And this also exposes why we really like to work with such diagrams, because if I write this out as an equation, it looks something like this. So this equation corresponds to my diagram where we have these inputs x, so those are my input units. Those are transformed via the weights in my first layer to the activations. So the activations of the first layer, and those activations are in turn transformed via the activation functions into the corresponding hidden units. So each node, each value over here is called a hidden unit. Then let me use a different color. Then the next layer gives me the values of the next hidden unit. And these hidden units are again used as input for the next layer. So a linear transformation followed by this activation gives me the activations and the hidden units at layer 3, which is then again linearly transformed followed by a final activation. And this gives me my outputs y. So this is my neural network written out, and it's nothing else as a stacking of linear layers, linear transformations, followed by a pointwise nonlinear activation. And I'm just putting this out here as a reference. Sometimes it's more convenient to work with this notation, where this O dot or this circle denotes function concatenation. So I'm concatenating a linear transformation with a nonlinear one followed by a linear by a nonlinear one. So this circle means function concatenation. Yeah, okay, it's just for convenience. Sometimes we write this, sometimes we write this, but quite often in this course we just show the diagram and then focus on specific parts of my neural networks and write those out. Okay, and then it becomes easier to actually design such neural networks, to become creative in how we actually transform my inputs in the end to a particular feature vector that is used for classification or regression. So we can allow for skip connections, for example. And these skip connections follow the same principle. So it means that each input unit can contribute to another activation by just taking linear combinations of these hidden or input units, and they can skip a layer, which means in this case that the activation of the units in this layer is formed by taking linear combinations of my hidden units at the previous layer, plus taking linear combinations of my inputs. And we could decide to give such a layer, such sets of weights, its own index 4. I think we would still refer to this as a 3-layer neural networks because it has these, as a function of depth, it has these 3 trainable layers. And this is what we call a skip connection. So this is what we refer to as a 3-layer neural network with skip connections. And sometimes we make these choices of skip connections because it is theoretically motivated. And sometimes we just do this because we empirically found that it is useful to do such a thing. Either way, we are allowed to be creative with how we design our neural networks. This also means that we can decide not to connect every node, every unit with with all the units in the next layer. For example, here we omitted, for example, this connection and this connection. So these connections are omitted. And this leads to what we call sparse neural networks. So sparse neural networks. And also this is a choice that we can make. And sometimes we make this choice because it's convenient, because we don't have too much processing power and we want to sort of reduce the computational load. So we sort of remove some connections leading to a sparse neural network. But sometimes we also want to impose a particular structure. And we can do that by, well, selecting which nodes connect to the other nodes. And this is particularly so the case when we talk about convolutional neural networks, which have additional weight sharing. So apart from deciding where to place connections, we can also decide to assign the same weights to a particular set of connections. So in this example, for example, the blue connections all have a weight 1, the green connection all have a weight 2, and the orange connections all have a weight 3. So this is what we call weight sharing, that there are multiple connections, multiple weights that essentially share the same weight. So this means that we can define convolutions also via neural networks, where we recognize maybe this convolutional structure here by moving this pattern of weights to the next node. So we see that at every feature vector is obtained via a linear combination of a local neighborhood, and this local neighborhood shifts. Now this convolutional structure is best explained with an extra visualization. Let's first of all start out by denoting such a linear mapping from input to the next activations via matrix vector multiplication, right? So we have, let this be the vector of all my input units, and let this be the vector of activations. Then each activation, for example, activation A1, is obtained by multiplying all these weights, so all the connections to A1 with, the input vector. So we have this row vector multiplication. And then in the next activation is obtained also by this row vector multiplication. So this entire stack of activation can be obtained via this big matrix. So you have all these weights that fully parameterize basically all possible linear maps from input to the next layer. And we're now going to turn this into a convolutional form. So convolutions are applied to structured data on functions on some axis. So now, for example, we consider a 1D signal. So it assigns for every time point on this axis. So let's just index it. So with a 1 to D. So I split this signal into D values. So each point on the signal represents one value x1. So let that be your input unit, input vector. Now what a convolution does, you apply this convolution kernel at every location. So we take a linear combination of my neighborhood values, and that gives me the new value for my output vector, for my output signal. So let me write this out. So when we consider my output vector A to be obtained by this convolution, or correlation actually, with a correlation kernel W, then the jth component of this output vector is obtained via sum over some neighborhood. Let's denote it with y minus j. So this distance smaller than k, so k is some kernel size. This is a smaller than. Okay, the sum of the values within this neighborhood with a set of weights that are aligned with my data point I. So this is my shifted convolution kernel W. So this correlation or convolution looks like this. So I move my set of weights, my kernel around, and every time I take this inner product, I multiply this weight with my signal over there. So I have 3 weights over here, and that gives me the signal at this point. Okay, so that's what's happening. In order to obtain the value for my output at this location, I multiply this kernel, these weights, with the underlying input x for this small neighborhood. Okay, so that's what you see over here, right? My first output value, so somewhere over here, is obtained by multiplying these weights with the first couple of input data points. Then I move to the next data point, and then I shift my weights accordingly. And basically it means I multiply the rest with zeros. But then my output A2 is obtained via W1, W2, W3 times X2, X3, X4. So I shift my kernel all the time, and that's what you see in this matrix. Okay, so what you see is that this convolution operator is essentially a matrix vector multiplication with an incredibly sparse matrix. So there's a lot of zeros, so that also means there's a lot of multiplication and computations that I do not need to perform. And then on top of that, we have weight sharing. So these weights are shared over this diagonal band, which corresponds to a shift of my kernel. Okay, so this leads to an incredible reduction of parameters that we need to train, but maybe more importantly, it preserves the structure of my signal. If my input represents some signal, then I want to preserve maybe this structure, because then I can apply this weight sharing. So convolutional neural networks are a specialized type of neural networks that are super efficient with the parameters, and that also contributes highly to the success of convolutional neural networks. Most applications nowadays are built on top of these convolutional neural networks. So when we have such structured data structures, we do not want to fully parameterize my neural network, but only work with maybe a sparse set of connections plus weight sharing. Okay, enough about convolutional neural networks. So in general, we have these feed-forward architectures, and we can be very creative in how we design this. Sometimes we want to design it because we want to preserve data structure, meaning that maybe we want to sparsify our network and apply weight sharing. So we can decide not to connect every node to every other data point. We can also decide to put the same weights along several edges, and we also may decide to put skip connections in our network. Okay, so anything is possible really as long as you form these units, these hidden units at some layer exclusively by taking linear combinations of units of lower layers. So really we want to preserve this feed-forward mechanism, because once we start including closed cycles, then we have some dynamics that can become very unstable. And so generally that's not what you want. And it becomes actually computationally impossible to work with this. So these ZJs can be any hidden unit from one of the lower layers. So that wraps it up for neural networks. So now we know what they look like, what they are actually, and how to construct them. So in the next videos, we're going to explore what we can actually do with neural networks. One of the main reasons for the popularity of artificial neural networks is the flexibility of the approach. It turns out that neural networks can represent basically any function that you want to approximate to any precision, of course given enough model parameters. Now this is a fact given by the universal approximation theorem. And essentially it says that we can use neural networks for all sorts of problems where we want to recover complex function mappings from input to output. And so far we, for example, have been very much interested in finding such mappings from input to output in the context of regression and classification. Now this slide shows the universal approximation theorem. We're not going to use this video to prove this theorem. We're just going to use it to gain some understanding and see what this theorem actually implies. So let's start off by reading what it says. So first of all, we're dealing with function f, so that can be any continuous function on a compact area Rd. And this will be the function that we're going to approximate with a neural network. Now such neural networks are based on these linear layers and activation functions, and let now this h be the activation function. So the activation function of my neural network, which can be anything, but it cannot be polynomial. So that's the only criteria that we have. So what we then consider, we consider a two-layer neural network, as we've seen in the previous lecture. And we're going to use this neural network to approximate this function that we started off with, right? And we're going to approximate it to some precision epsilon, so some small positive number, such that for every point x, these functions are very close to each other, where closeness is given by this small number epsilon. Then this theorem says that there exist two-layer neural networks that can become arbitrarily close to my function f that I want to approximate, where closeness is controlled via this epsilon parameter. And this means the smaller or the higher my precision, the more number of hidden units I need. But it is possible to find such a number of hidden units that allows me to construct such a model that comes arbitrarily close to my function. Switching back to this basis function viewpoint, my two-layer neural networks learn these basis functions phi m of my input x. And so basically these construct complex feature vectors, which in turn are used in this linear model, and that is given by my two-layer neural network. And this two-layer neural network can then be arbitrarily close to the function that I want to approximate. Now I want to gain some intuition of what this theorem essentially tells us, and I'm going to do that by starting off with ReLU-based neural networks. So basically this theorem says I can choose any activation function I like as long as it isn't polynomial. Now the ReLU, so the ReLU was this max of 0 and a, So with the ReLU, I can also come arbitrarily close to any function that I want to approximate. And I'm going to show that as follows. First of all, recall that this first layer can be interpreted as generating these basis functions, right? I have m of such basis functions after the first layer, and these basis functions are defined via m of such linear mappings that are then pulled to such a ReLU activation function. And this ReLU makes sure that all these values become positive. Okay, so I have m sets of weights. Now let's take a look at the 1D case. So let's suppose my input is one-dimensional. Then what my first set of linear weights does, it assigns some slope. So it creates these linear functions by multiplying x with the weight of my first basis function in the first layer plus some bias. Okay, so that generates this linear function, and then I apply a ReLU to it. So I'm only going to take the positive part of this. So that means that everything below 0 is mapped to 0 actually, and that actually gives me then my first basis function. So this would be phi 1 of x. Okay, now let's consider a different m. So basically the next activation in my first layer. So suppose maybe this one has a negative slope. So it would generate this linear function given by W2, so that was my second activation of the first layer times x, so that's the slope, plus some bias. Okay, and also this one is then activated with the ReLU, which truncates everything at 0. So if I take the ReLU of this thing, well, we got this positive basis function. So this would give me phi 2 of x. Okay, now let's consider also a third basis function, which maybe has a slope and a bias, which creates this linear function over here, which is also truncated at 0 via this ReLU activation function. So that will give me the third basis function. Okay, so what I just drew was this first layer, right? So these linear components, I had m is 3. I had 3 of such basis functions in the end that for every x provide a particular activation. Then what happens in the next layer is I'm going to take linear combinations again of these activations. So essentially linear combinations of these basis functions. So that allows me to give a response for every possible x. So let me draw that what's happening here. So that means also my final output is going to be a function of x. And it will be given by the weighted sum. So really this linear combination. So I assign a weight in my second layer to each of these basis functions. So that's what my output is going to look like. Okay, now let's move from left to right. So on the left, we only have really one basis function that is active. And let's just give it like a positive weight, weight 1. So I really replicate this basis function over here. Then my function remains 0 for a while. And then this particular basis function kicks in. Let's also give it a positive weight. So, well, the function starts increasing. Then this particular basis function kicks in. And let's assign it a negative weight. So if I add this slope, well, make it negative. Let's subtract this slope to this one. Then maybe the function starts to look something like this. So essentially what is happening here, that with such ReLU-based activation functions, I create basis functions that look something like this, that are only activated for particular values of x and are 0 otherwise. And then if I start to make linear combinations of these basis functions, then I get the result that my resulting functions, they will become piecewise linear, where we transition from one linear piece to the other. So here I have a linear piece, here it's constant 0, here I have a linear piece, and here the transitioning between these points take place at the locations where my basis functions become active. Okay, so that's the core idea behind neural networks with ReLUs, that I'm able to construct functions that are piecewise linear. And then the universal approximation theorem says that I can use these piecewise linear functions, so these two-layer neural networks, to approximate any function to arbitrary precision. So let this be the function that we want to approximate. And let this, for example, be the epsilon interval which we need to stay within. So that defines the regions that I'm allowed to pass through with my function. Then if I'm going to approximate this with a piecewise linear function, I could do something like this, like a segment over here, over here, over here. So in that sense, I can approximate this function with only 3 basis functions. Now, if I'm going to reduce the interval, so I make epsilon smaller, then I have to stay close to my data, or I have to stay close to my signal that I want to approximate. Okay, then I can basically work with more of these piecewise linear functions. And in this particular case, I need, let's say, 1, 2, 3, 4, 5, 6, 7, 8, 9 basis functions. So with m is 9, I can now approximate my signal to a closer precision, so for a smaller epsilon. Okay, so this is a sort of visual proof that I can approximate any continuous signal with just these piecewise linear ReLU networks up to some arbitrary precision. And if I want to approximate this closer and closer, I basically need more and more of these basis functions. And with more basis functions, I need more and more hidden units. With this m represented the number of hidden units in my 2-layer neural network. Okay, then it follows by induction that deeper neural networks also have this property. And then we can talk about what is the most efficient way of starting approximating or constructing these complex functions. And let's consider the following. Let's say we have a neural network with L layers. So this is a deep neural network. Then we can approximate this deep neural network with a shallow neural network, let's say with only L prime layers, because that's what our universal approximation theorem says, right? I can approximate any function, so also this deep neural network with a shallow neural network with only L prime layers. Right, and I can approximate this deep neural network then with the shallow neural network up to some arbitrary precision parameter epsilon. Then it turns out that the number of hidden units that I need to approximate this deeper neural network scales exponentially with decreasing epsilon. So if I want to be more precise, I need an exponential growth in the number of hidden units. And this in turn implies that approximation with deep neural networks is more parameter efficient. Now maybe let's take a second thought on that in the context of these ReLU networks. So in ReLU networks, we saw that the expressive power of such a ReLU-based deep neural networks is associated with the number of linear regions, right? So because we have a ReLU network leads to these piecewise linear neural networks, and well, the more pieces I have, the more accurate my predictions or my approximations become. And the number of regions that I can represent with ReLU-based deep neural networks scales with the width. So it scales polynomial in width, but it scales exponentially with depth. And in this case, this d is the input dimension. So the most efficient way of gaining more region is not to widen my network, so to add more hidden units per layer, but simply to go deeper and consider more layers, right? Because then let's say I have a fixed number of parameters that I can spend and I can distribute them over my network, design different networks, so I can make choices. And the number of parameters as a function of width scales quadratically, because in these neural networks, I want to connect every input to the output of the next layer. So that's, let's say, width times width, number of parameters I need there. And then for each layer, I need this quadratic number of parameters. So my total number of parameters is given by width squared times depth. So when I'm then told, okay, this is the number of parameters that you can spend, now make your choices based on the width and the depth of the networks, then, well, it's clearly that most expressive power is gained by going deeper with maybe less neurons per layer, so with less hidden units per layer, than staying shallow with more neurons per layer. And then this also explains the popularity of deep neural networks versus shallow neural networks, simply because these deeper neural networks were able to perform more complex tasks. And this was sort of empirically discovered, but it was also theoretically proven via such statements. So building deeper neural networks is better in terms of expressive power and the type of problems that you can solve than staying shallow. Okay, so let's take a look at some examples of such function approximations. Maybe first of all, what kind of problem does this correspond to? Are we now talking about classification or are we talking about regression? We're talking about regression, right? Because our objective is to map any input to a corresponding output value. So these input-output pairs are now given via my ground truth function, f of x. So in this particular case, f of x is x squared, and we sample 50 points of this. So these are these blue dots, so those form my input-output pairs, which we're going to reconstruct with a neural network. And our neural network is a 2-layer neural network with only 3 hidden units and a tangent hyperbolic activation function, and only 1 linear output, right? Because I want to predict this particular value. So my neural network really looks something like this. So I have my input x, then we have this hidden unit. So I have only 3 hidden units. So this would be set 1, and I apply a 10H on these activations on these hidden units. And these are then combined via my output weights, so W2, to my prediction. Okay, and recall that these hidden units, like just before the output layer, take on the interpretation as my feature vector, right? So these hidden units as a function of x for my basis functions, that I can use to obtain my final prediction. And you see, with only 3 of such basis functions, we can take linear combinations of these to form this parabolic shape over here. So we actually have a perfect reconstruction. Now figure B is then, we're trying to approximate a sine of x. And also here we see, nice, so that's really nice, this idea that we're learning these basis functions. And with these 3 type of basis functions, I can assign weights to these basis functions, and that would give me the sine reconstruction. Now these are nice, smooth, continuous functions, but we can also approximate, for example, the absolute value of x, and then we have this a sharp transition going on over here. So overall we have a good approximation, but we see that the approximation wiggles a bit, and here it takes a shortcut. So of course we make some errors, and this basically implies that we need more hidden units to also represent these sharp details. And then in figure D, we try to approximate the Heaviside step function hx. So it really takes on the value 0 below this threshold, and then it jumps to 1. So also, again, a very sharp transition. So we see that now actually our neural networks learns these basis functions that are also on or off at particular regions. And, well, a linear combination of, well, these basis functions then allows me to make this step function approximation. So these are just some examples of functions that we can approximate. And in practice, that's also what we're doing with regression problems, right? We want to recover some function mapping. We do not know it, but we have these input-output pairs, and that's what we recover. And basically, our universal approximation theorem says that, well, if my network is deep enough or if it's wide enough, at least I would be able to represent it. And now the challenge is, of course, to actually find this particular model. Using, for example, gradient descent optimization of some loss. I'll talk about it in the upcoming videos, but that's essentially what we're doing here, function approximation. Okay, and then I want to give this example again, go back to this ReLU approximations, because I really like this idea of piecewise linear function approximation, and the idea that we have these basis functions that are learned in this process. So this is the result if I want to approximate the sine wave with a 2-layer neural network with only 3 hidden units. And so this is when I trained it and it converged. And this is, for example, what I start off with. So I initialize with some random weights and biases, and then I'm going to minimize some loss function. So I make all these errors and I want to minimize these errors. And that's a criterion that I'm minimizing. And then I apply some iterative scheme over here, and you see that my basis functions start to adapt to something useful, right? And we also see that the points where these piecewise linear functions transition exactly take place at the point where my basis functions are active or inactive. Okay, but it cannot come perfectly close, right? Because it's too simple a model. For example, especially here, I'm making some errors. So if we really want to improve our representation or approximation, then we really should increase the number of hidden units in our network. So that's shown over here in the right figure, right? So let's say I initialize my model randomly with a set of weights. So each, let's say, basis function gets its own slope and offset. And then I start this learning process, and I'm going to optimize my weights iteratively. And you see it nicely converges to the actual signal. And again, we see that we actually have learned all these nice basis functions with a particular slope and a particular offset, like an on-off location, and that determines these transition points. Okay, but this is just essentially another example of my universal approximation theorem at work. Where, of course, it's the fact that I worked with ReLU activation functions to obtain these nice piecewise linear approximations. So all this was talk about regression essentially, but function approximation also takes a role in the classification with neural networks, right? So let's suppose I have this data and it's drawn from some underlying distribution, and these underlying distributions determine a true decision boundary. So that's what you see in green. So in green is what you see where the true posterior distribution for X equals the posterior distribution for class 2. So these decision boundaries are essentially obtained as the zero level set or some level set of a function that we are now going to approximate. Okay, so this is then a classification problem where the blue points correspond to class 1, for example, and the red points correspond to class 2. So then again, let's think about what we're doing. So we're, how many inputs do we have? Well, we have 2 inputs. We have this 2-dimensional data set. How many output units do I need? So I'm now designing my neural network, right? So how many output units do I need? Right, I actually only need 1 output, right? Because I have this binary classification task. So the probability for the other class is given by 1 minus my probability for the first class. I could still encode this with actually 2 outputs and then work with a softmax, but this is completely unnecessary, right? It's a waste of parameters. So I only consider 1 output, and I'm just going to make the choice to work with only 2 hidden units. And I'm going to work with a 10H activation function. And because I'm considering classification, my neural network should spit out a number between 0 and 1, because my prediction should represent some probability. So my output activation is going to be sigma, the sigmoid. Okay, so then my objective is really to recover this true posterior distribution. And okay, now I'm training this neural network, and this red line is what comes out. So this red line is obtained via my 2-layer neural network with only 2 hidden units. Okay, so this is a very simple approximation. It does make this division quite okay, but if I want to really improve on this, so essentially if I want to reduce my epsilon in my function approximation, recall that I'm approximating this function now with a neural network, then essentially this tells me in order to represent such complex shapes, I should increase the number of hidden units. Okay, to conclude, we can formulate regression as well as classification problems as function approximation problems, where in the regression case we really want to recover the true function mapping between input-output pairs, and in classification we can consider it as approximating my posterior distributions. Then the universal approximation theorem then says that if I go deep enough, or if I have enough hidden units, then at least I would be able to represent this true function. And now the challenge is, of course, to actually find this function. So now we're talking about optimization and minimizing error functions. And that's going to be the topic of the remaining videos on neural networks. Now that we've familiarized ourselves with the concept of neural networks, let's try to actually do machine learning with it. Now, the starting point of any machine learning task is to describe the problem that you're going to solve and define how you are going to quantify the performance of your algorithm. Or put differently, you need to define a loss function or an error function that you want to minimize. Now, in this video, we briefly summarize the choices you should make when working on regression and classification problems with neural networks. So the setting is that we are provided with this data set of measurements of data points, and we want to do something useful with it. And in regression and classification problem, we also have targets associated with it. But the point is, we have this data, we want to do something useful with it. So we're going to design these neural networks that map these inputs to some output. And we can make a very complex design over here. That's up to you, be creative with it. But now we're going to focus on the outputs and optimizing, or actually training such neural networks. We're going to focus on how to find these W's. So the general steps is define the number of outputs. This is basically given by the problem that you're going to solve, multi-class classification or regression. So that defines the number of outputs. We also need to define an output activation function. I'm going to say in the next slide how we are going to choose the output activation functions. But all of this is really motivated by what kind of loss function we're going to minimize. Now in this video, we're going to use a probabilistic interpretation of the network outputs in order to make decisions on these choices that we need to make. And these choices depend on the problem that you're working on, right? So now let's first consider the regression problem. So the setting is we have all these input points. So each input is a d-dimensional vector, and we want to map them to a corresponding target. And this corresponding target can take on any value on the real line. So now again, we resort to this probabilistic interpretation. So we have this true model that we want to recover that maps every x to a particular target t, but we have measurement noise, so we have uncertainty to take into account. So instead of making just one point prediction, we consider uncertainty in our predictions with these assumed target distributions. And so far we've been modeling these target distributions via Gaussian, so via normal distribution. So the probability for a given target, given my input parameters, is parameterized by this mean. So this is the model that we want to recover, and there's some uncertainty on my predictions because I know my measurements aren't perfect. So that's described by this variance or inverse precision. But essentially we're making a prediction, so this y, that's the model that we're going to recover, and that model's really the mean of my predictions. And now in this neural network setting, this thing is precisely the thing that we're going to model with a neural network. Okay, so that's the problem, that's the overall strategy. And then so then we're building a neural network that maps a single, a multi-dimensional input, so a d-dimensional input, to a single target. So that also means that I need one single output unit, which is given by so that's my final output activation, and I need to make a choice on what activation function I should apply to my final output activation. And since my targets are real valued, so they can take on any value on the real line, maybe I do not want to apply any activation function because, well, this activation of the output is already some number somewhere on the real line. So when we talk about regression, we usually do not apply any activation function to my output. Okay, so that defines our neural network. And then now, since we consider this in a probabilistic setting, we assume these target distributions. And then, of course, we want to maximize the likelihood, which corresponds to minimizing the negative log likelihood. So the error function that I want to minimize, such that I get an optimal model, an optimal neural network, is given by the negative log likelihood. Okay, and now we've seen this thing before, right? So we take the log of this normal distribution, essentially, and that gives me this quadratic term. And these are factors that do not contribute to my error as a function of W, right? So equivalently, we can minimize this sum of squared errors. Now let's take a look at the case of binary classification. So we have these input vectors, again, d-dimensional, but now my targets can only take on the values 0 or 1. And again, we adopt this probabilistic viewpoint on things. So we are going to say that my outputs, So my model, this is my neural network. So this is my neural network, that it models the probability of my target taken on the value 1. So again, we assume a target distribution which we want to model, and we're now modeling the Bernoulli distribution essentially. So my model spits out the probability for class 1, and that also implicitly gives me the probability for the other class. And then we can use these labels T to have this selection mechanism over here, right? So this is essentially a Bernoulli distribution, which gives me the probability for class 1 versus the other class. Okay, so then if I have to decide my output layer, how many neurons to put there, how many units, so we're really assuming a single target, which represents my the probability for class 1. So my neural network only needs one single output unit. So here denoted with A out, and we need to apply some activation function to it. Now, what would this activation function be? Now, the targets are binary, and the targets represent probabilities. So the output, my model spits out a value between 0 and 1, or that's what it should do. And that's why we're going to rely on the sigmoid activation function, because my model should represent the probability for the target being 1, and it should take on values somewhere on the range 0 to 1. Okay, so that motivates why we should use the logistic sigmoid. Now again, because we adopt this probabilistic approach to modeling, the natural choice to quantify how well my probabilistic model performs is really to take a look at the likelihood, right? The likelihood that my probabilistic model actually describes the data, or the other way around, that my data is described by such a probabilistic model. So we take a look, we want to maximize the likelihood, which corresponds to minimizing the negative log likelihood. And for the logistic sigmoid case, the log of my probabilistic models boils down to the cross entropy loss. So I want to minimize the sum over all my data points, the target Tn times the log of my model plus 1 minus, so that's really the target for the other class, the log of 1 minus y xn. So this is my model. Okay, so when we're doing binary classification with neural networks, then my output is a single output, which is activated via the logistic sigmoid. And as loss function, we're going to minimize the cross entropy loss. All right, and then of course we can also consider classification with k classes. So my input is again a d-dimensional vector, but now my target is also a vector. So for each data point n, I have a target that looks like this. So tn2, tnk, where each of these targets for each class, so for each data point n, I have k of such targets, which take on the value 0 or 1. And this was what we call the one-hot encoding of my class, right? So with a one-hot encoding, only the target for my kth class takes on the value 1 and the rest is 0. So this is a one-hot encoding of the kth class. So the one-hot encoding really encodes these true probabilities, right? So if it represents the kth class and the probability for all the other classes is 0, but it's 1 for that particular class. And now we want to recover such probability vectors. So we want to really predict for each input x, the corresponding class probabilities. So we want to sort of model this target distribution, and this target distribution is then a generalized Bernoulli distribution. So let me write that out. So it's really the product of all probabilities for each class, but selected via this one-hot encoding, right? So if I'm considering the kth class, then only the kth model is active, right? So that gives me the probability for class k. So that's what we're trying to recover. So this probability distribution that we can test for every class k, we can check what the probability is for that class. So that's essentially given in this form. where each yk represents the probability for that class, and the particular distribution that you see over here is typically referred to as the generalized Bernoulli distribution. Okay, so this means that now I have k targets, right? I have k of these probabilities that I want to predict. So this means if I want to design my neural networks, I should design it in such a way that it has k output units. And these output units represent the probabilities, and they're obtained by applying some activation function to my output activations. So now we're considering we want to predict probabilities. So that means that the sum over all my probabilities should equal 1, right? So this is what I want. I want the sum over all my classes. So the probability for class K given my input X, which is modeled via my neural network. I want this sum to sum up to 1, and this is ensured by the softmax activation function. So we saw before that this is the generalization of the logistic sigmoid, right? With multi-class classification problems, we can always formulate our probabilities in the context in the form of such a softmax function. Okay, so that really describes my overall model architecture. I want to predict k output units, and I want to use the softmax activation function to really obtain my final probabilities from the output activations. And now the corresponding error that we want to minimize is, of course, again going to be the negative log likelihood of my probability distribution. And that in this softmax case, again, it gives me the cross entropy loss. So I'm going to sum over all data points. So from n is 1 to n. And then I'm going to sum over all my classes the true target, tnk, times the log of my prediction for that particular class. So this is the cross entropy loss. This is the cross entropy loss associated with the k-dimensional generalized Bernoulli distribution. So this is the loss that we're going to minimize. Okay, this then summarizes what we did, right? So we considered regression and we considered classification, and now we want to design neural networks and define the loss functions that we want to minimize. Now in the regression case, in all cases we approach this from a probabilistic viewpoint. Now in the regression case, we assume a Gaussian target distribution because there's uncertainty in my predictions. And then I let my neural network make a prediction for the mean of these distributions. And so that actually also tells us, because this mean can take on any value on the real axis, that my output activations, I have one output activation, and it's activated with the identity activation function. And these ingredients together then tell me if I want to maximize the likelihood associated with this target distribution, I'm going to minimize the least squared error. Now for binary classification, we assumed a Bernoulli target distribution. So my neural network makes a prediction for the probability for class 1, and then the probability for both classes is given by this Bernoulli target distribution. And this also tells me that we want to work with, as output activation function, we want to work with the logistic sigmoid. So these ingredients together tell me that my loss that I want to minimize is going to be the cross entropy loss. And likewise, in the multidimensional case, we assume a generalized Bernoulli distribution for k classes, and my neural networks makes a prediction for each of these classes. And to ensure that my output predictions are indeed can indeed be interpreted as probabilities, we need to apply a softmax function on all these output predictions. And then again, we want to maximize the likelihood, and this eventually boils down to minimizing the cross entropy loss. Now that we know how to design neural networks and are able to define the loss that we want to minimize, let's recap how we can minimize losses via stochastic gradient descent. In this video, we're going to look at what it means to perform stochastic gradient descent in the context of neural network training. Now the setting is that we have just defined our neural network. So we know how many output neurons I I need, and we know which kind of loss I have to minimize. This could be, for example, the least squares loss in regression, or the logistic loss or the cross entropy loss in classification problems. And now our objective is to find the most optimal set of model parameters W that really minimizes this arrow function. And so far we have been really lucky that our arrow functions were always convex. So that meant that if we apply some gradient descent method or whatever alternative, we always end up with a globally optimal set of parameters that really globally minimizes my arrow function. But now with neural networks, with these complicated functions, which are highly nonlinear, I no longer have this guarantee that my arrow function is convex, which means that I can expect to observe several local minima in my arrow landscape. And that is depicted over here. So this is my energy landscape, and let's say I have two of such valleys. Local optimal locations are these. So if I now apply gradient descent and I start at this point, for example, and I walk downhill, then I may end up in this local minimum, and there's no way I'm going to get out of it because I just follow the gradient downhill. At this point the gradient is 0, and in my surroundings all the gradients point upwards basically. So there's no way I'm going to escape my local minimum over here. And I do want that because I want to go to the most optimal set of parameters. So how do we reach this global minimum? Now the short answer is we can. There's no way we can guarantee that we will end up at a global minimum. But we can try to avoid local minima as much as possible, and we are going to do this via stochastic gradient descent. I'll explain this in a couple of minutes, how stochastic gradient descent helps with preventing to getting stuck in local minima. But the challenge here is we are dealing with an arrow function which is not convex, so we have to deal with local minima. Now, by far the most popular technique for optimizing or minimizing arrow functions in deep learning is via stochastic gradient descent. And there's reasons for its popularity. First of all, it has a very simple update rule. Maybe this one, because in stochastic gradient descent, I only approximate my gradients with one data point or maybe a few data points. So it has a very simple update rule, efficient to compute, but it has some properties that also prevents the gradient descent of getting stuck at local minima. But before we get there, let's review what gradient descent does. So we start off with an initial estimate of my model parameters W. So tau is my taught iteration. And then I'm going to find my new set of parameters W by walking in the negative gradient direction, right? Because the gradient point upwards and I want to go downwards. So I take a step in the negative gradient direction with some step size eta. And as I just explained, we're dealing with an arrow function that has a lot of local minima, so we quite easily get stuck at such a local minimum. So let's take a look at this figure, which I drew in preparation and which I'm now going to fill in. So the setting is as follows. So this gray region indicates some arrow function as a function, let's say, of two model parameters W1 and W2. And I'm interested in obtaining this point over here. So this is my globally optimal minimum. It's the lowest error value I can find for all possible W's. But then I have all these local minima, right? So initially, of course, I do not know what my optimal value will be. So I have to make an initial guess. And let's say I start off with this set of model parameters at tau is 0. So my initialization of the weights. Then what I'm doing with gradient descent, I'm going to make an estimate of this gradient, or actually with full gradient descent I actually compute the full gradient. So that's what this arrow indicates. And I'm going to walk downhill and then again check my gradient, walk downhill. Okay, so I walk downhill this energy landscape or arrow landscape via gradient descent, and that actually leads to the result that I end up at this local minimum. And of course, if I would put my initialization somewhere else, so maybe let's say over here, then gradient descent will bring me to this local minimum. And if I put my initial weight over here, then maybe we would end up at the global optimal location. But because my energy landscape is is highly non-convex, I'm bound to end up at some local minimum. Okay, so that's the issue with regular gradient descent. And now we're going to consider stochastic gradient descent. And this means that, now, first of all, my error is a sum of all these individual errors. So that means I can also approximate my gradient by just computing the gradient for one data point. So the stochastic gradient descent method works as follows. So we choose some learning, some step rate eta, we initialize, and then we sequentially choose one point out of my dataset randomly and use only this point to update my weights. So that gives me an estimate of the gradient based on the single data point, and I'm going to use this gradient to update my weights. And of course, instead of working with just a single data point, I could also maybe average this gradient or take the sum of my error terms over a range of data points, m. So maybe work with 16 data points to approximate my error. And that is what you call a mini batch. So a mini batch of 16 of such data points are, for example, used to approximate the error. So I'm going to indicate that as follows. So I'm going to say that both of these provide me an approximation of the gradient. So I'm going to denote that with this tilde over here. Okay, so now let's see how that would work. I'm using this approximate gradient ID because now if I compute this approximate gradient at this point, for example, maybe it points in this direction because this energy error landscape looks slightly different for each data point. Maybe for one data point it's more efficient to change my W's in this direction, and for the other it's efficient to do this in this direction. So for every data point I would actually get maybe a different estimate of the gradient. So if I now do stochastic gradient descent, okay, I have a noisy estimate of the gradient. I take a step, I end up at this location. Again, noisy estimate. Maybe that's somewhere over here. Maybe for this data point, it's in this direction. Okay, so I have these stochastic updates. And of course, that has still the chance that I end up at this local minima, huh? But because my gradient estimate is so noisy, it could also be that at some point I estimate the gradient in this direction and take a step in this direction and then the next point. And so I am able to escape such local minima because these gradients, they look different for every data point. And that actually has the property that I'm able to escape local minima. And that could actually lead to the result that I will end up at another local minimum, which is even lower than what I encountered just now. Okay, so that motivates why it would be actually a good thing to work with approximate gradients via the stochastic gradient descent method rather than working with the full gradient descent. Okay, so to continue on this comparison with gradient and stochastic gradient descent. Well, first of all, both rely on this learning rate, right? And we saw that actually before in our video on gradient descent. So if the learning rate is too small, then basically it takes me a long time to end up at some local optimal location. And in the stochastic gradient descent case, moreover, it may be harder to actually leave such local optima because my step size are so small. So I always stay in this vicinity of this local optimum location. But conversely, if my step size is too large, then I completely jump over all these optimal locations and I will never converge to anything. So what people tend to do is they tend to work with a learning rate schedule. Like they start off with a high learning rate, so that quite quickly brings me somewhere close to, let's say, some optimal region, and then I decrease the step size. That brings me closer to the optimal location, and then a further decrease, so I really refine my optimal solution in the end. Okay, so these learning rate issues sort of both equally well apply to the gradient and the stochastic gradient descent method. But then apart from the possibility to escape local minima with a stochastic gradient descent, there's another motivation for stochastic gradient descent, and that's namely that they're much more efficient. So in order to compute this gradient, I only need to do this forward pass for maybe one or a few data points in my mini batch. So this is fast to compute. And if you would compare this maybe to the full gradient, especially at the beginning, all of these gradients roughly point in the same direction, because my initial solution is likely to be very poor, then that means there's also a very clear direction to go to improve my solution. And with this I mean, if I have, for example, my initial point over here, so this is W0, then let's say my true gradient points in this direction. So that would be my true gradient. And then I have all these noisy estimates. For example, for data point 1, the gradient for data point 1, for example, points in this direction. The gradient for data point 2 maybe in this direction, so that's a gradient of data point 2, maybe for another one in this direction. So I have all these, well, noisy estimates, but roughly they all point in the same direction. So especially at the start, I just want to have a course direction to follow, and then just estimating this gradient with one data point would be enough to get me going in the right direction. So if you compare this to the full error, which is based on all data points, this is very expensive to compute, whereas these gradients are only computed with a few or maybe even only one data point. So this is super efficient to compute. Okay, so that's summarized over here. I do not necessarily need the full gradient because all my gradients are roughly aligned. So I can also make an estimate with one or a couple of data points. And then we saw this point that stochastic gradient descent is more likely to escape a local minimum, since so if my total gradient would be 0, that means I'm not going to update my weights, but this does not necessarily imply that this gradient is the same for each data point, right? So if I visualize that again over here, let's suppose here I have a true gradient which is 0, but because this landscape looks slightly different for every data point, it could be that maybe for this particular data point my gradient looks like this. And that means I would take a step in this direction. And then again there I have some estimate. Working with these noisy gradients really allows you to escape local minima. Okay, so those are some strong arguments for using stochastic gradient descent over a gradient descent. But maybe then there's an argument against a stochastic gradient descent. So let's compare the two in a similar situation. So what you would do with a gradient descent, you would really directly walk downhill, and that would end you up at this globally optimal, or let's say some optimal location. Now what would happen in the stochastic gradient descent case, because I have these noisy estimates, I am probably going to take a very roundabout route to my optimal location. So I would need much more iterates to converge to a local optimum. But then again, the advantage of a stochastic gradient descent is that these gradients are super fast to compute, because I only need one or a few data points, whereas here I need to process my full data set. So the point of this slide is that stochastic gradient descent requires more steps, but each gradient update is fast to compute. Okay, but then there's one final but very important remark, and that is that because I have this non-convex energy landscape, my solution highly depends on how I initialize my model, right? So basically for every different starting point for my models, I may end up at a different optimal location. And one final solution to which I converge to might be more might be better than the others. And that's nicely visualized over here. So this is a plot of the test error. So test error. So the test error for different neural networks with a different number of parameters. So what is plotted here is the number of hidden units. So I'm training networks for different network complexities. So 10 means I have a lot of hidden units, so my network is complex, and therefore I can also expect more local minima in my error function. And this is a very simple model, and therefore I can expect a smoother or let's say cleaner or nicer error landscape. So then for each model, so for each model complexity, I randomly pick a new initial seed, so initial set of parameters W. And for my simple model, I see that all of these solutions of all these models, they converge to the same model with a particular, which give a particular test error. But if I go for the higher models, then my error functions are highly non-convex, so a lot of local minima. I see that my solutions depend a lot on how I initialize. So some initial W's end up converging to a very poor local minimum, so I still make a lot of errors. But some models, they are able to reach a very good local optimal location, and therefore they end up with very strong models. And that's sort of a general trend, right? So with local minima, you have more stable optimization methods because there's not much model complexity and not much variation really among my models. But if I go to very complex models, then I tend to end up at local optimal locations. And then really the difference between this very complex, good working model is there with the same complex model, but now with a poor solution. So we have these high variations in test error. Okay, so this also means that always, whenever you report your errors or your performance scores with neural networks, you should always rerun your training procedure with different initializations of W. Because if you run it once and you end up with a model which is very accurate, then you report it and you say, hey, yay, I got state of the art. But maybe then someone re-implements your method and then discovers, but wait, that you were just very lucky. I actually end up with this model. So be fair about the numbers that you report, and also report uncertainties on your performances. So the message is, so always run with several initializations, because this allows you to gain some understanding on the uncertainty on your models. Okay, so that wraps it up for neural network optimization via stochastic gradient descent. Currently, stochastic gradient descent is really the method to optimize your neural networks because they're so simple and they have these properties that, well, they have ways of escaping local minima. But still, this is not a guarantee that you won't end up at local minima. In fact, you're super likely to end up with a local minima, and that leads to the fact that you also can expect variability in your models. The most popular way for training neural networks is via stochastic gradient descent. This optimization method updates the weights iteratively based on the gradient of the error that we want to minimize. Now in this video we are going to explicitly write out how to compute the gradients in neural networks. And it turns out that even though neural networks can be incredibly complex, the computations of gradients themselves is actually quite tractable because it can be sequentially obtained via a consistent application of the chain rule of differentiation. Now, just as the activations in a forward pass can be computed by evaluating the activations layer by layer, also the gradients in each layer can be sequentially computed by backpropagating the errors from the last layer all the way down to the first layer. Now, since the multidimensional chain rule plays such a central role in this optimization framework, let's take a look what it actually says, this multidimensional chain rule. We use this rule when we have to deal with multidimensional functions, so that it's a function of multiple input parameters, and each of these inputs, let's denote them with g indexed with some subscript d, each of these inputs is in turn again a function of another input. So let's put it like this. So we have all these, let's call them coordinates. Each coordinate depends on some parameter x, and my function f is again a function of these coordinates, right? Now, if I want to compute the derivative of such a function with respect to x, so let's say is the lowest parameter in the hierarchy, then we have to apply the chain rule as we've used to, but now we work in this multidimensional setting, so I have to take into account the influence of a change of parameter x on all these input parameters. So that's roughly what it says. So I'm taking the derivative of f with respect to x, which can be thought of as the influence of a small change in x on the value of f. then the change that this a small delta x change induces is going to be a sum of the effect of changing x that it has on the d coordinate times, and this is the chain rule essentially of f with respect to that particular coordinate. Right, so all these changes on these coordinates add up via the chain rule to a total change on my final function f. Okay, so that explains the multidimensional chain rule. Now let's try to translate this to the context of our neural networks. First, start off by recalling that my neural network is actually a nested function. It's a function after function after function, roughly looking like this. So I have a neural network as a function of an input x, and it's obtained by, let's start on the right, so by first applying this linear transformation in the first layer on x, so that gives me the activations of the first layer. Then we apply some nonlinearity to it, then again some linear transformation of the second layer, then again some activation function on it, and so on. So this means if we were to compute the derivative of this neural network with respect to x, we have to apply a chain rule over here, right? So to propagate the errors, like the small changes that my x have on a to h to a to h, all the way to the effect of my the effect that it has of the small change on my final output. Okay, now also recall that my neural networks, like these functions, are multidimensional functions, right? It's mappings from an input vector to an output vector. So this f could, for example, be one single activation, let's say the activation at layer L, and this activation was given via a linear combination of all the activations of the previous layer, right? So if L minus 1, which again is a function of x, we have the activation number 2 at layer L minus 1, which is a function of x. And so we have all these activations. So you see that the activation unit 1 at layer L is going to be a function of all these previous activations, which are in turn a function of the input x. Okay, so each activation is a function of previous activations. Okay, so that's denoted over here. So my f could be my first activation, and it's going to be a function of all these activations at the previous layer. Okay, and that then tells me that if we want to compute derivatives, these multidimensional derivatives and chain rules, we have to rely on this particular formula, which we will get back to at the point where we actually start using it. But for now, remember, this is the multidimensional chain rule. You should really remember this formula. Then the setting is as follows. We have designed our neural network, which is designed to transform an input to a particular output. So we make some decisions on the output, for example, and now my output is used to compute an error, right? So this output really defines the error, and then I'm going to compute the derivative of this error with respect to this model parameters w. So I apply some gradient descent method, for example, to update my weights based on the error that I computed, right? So I need to evaluate the derivatives of my error with respect to these weights. So, and then I just said that I'm going to need to rely on the multidimensional chain rule, right? Because if I want to measure the influence that this W has on the error, it has to propagate through all these layers up to my error. So I'm going to need this chain rule. Now let's think about the flow of information. So what we're actually doing, so we have this input, and this input information propagates forward, right? So it's used to compute the activations at the next layer, and then we again compute it at the next layer. So essentially the information at layer L is obtained by looking at information that was available at the previous layer. And we use this very simpler rule that we just work with these linear transformations followed by applying this activation function to each activation, and that would give me the hidden units at that particular layer. Okay, so this is called forward propagation, really the propagation of information from the input all the way to the output. And in this process, we are essentially computing all the possible activations at the hidden units. Then what we're going to focus on today is going to be backpropagation. So the backpropagation of errors. So again, once I've done this forward pass, then I know what my outputs are, I know what my error is, and that allows me to essentially compute a gradient in the end. And I'm going to start off with by computing the errors or the derivative at this layer, and I'm going to propagate these gradients all the way back to the first layer using this chain rule of differentiation. So that's the task of backpropagation. The goal is to compute all derivatives. Because recall that it is our objective, right, to in the end have access to all these derivatives, because those can be used to update my weights via stochastic gradient descent, for example. Okay, so that's what we're going to do. We're going to compute all derivatives of my error function with respect to my model parameters, and I'm going to evaluate this error based on some data point xn. Now it is important to realize that if we consider the derivative with respect to, let's say, this particular model parameter wji, then it's important to realize that a small change of this parameter leads to a change in the results only via this activation over here. So it only induces a change through this particular activation. So this means that I can compute this derivative with respect to wji by the chain rule, right? Because it only depends, this error only passes through this jade node. So I have to compute the derivative of my error with respect to this jade node. Let's mark that in red. And then of course the chain rule, I also need to compute the derivative daj dwji. Now the computation of dA to dwji, that's simple enough, right? Because we have this simple relation over here. It's just a linear combination of my previous activations. Then the tricky part lies into the computation of this derivative of my error with respect to the jade activation. Because this jade activation, this one, is used by all other nodes downstream connected to it, right? So changing this particular activation has an influence on all these other activations, and therefore it has a more intricate contribution to the final error. So for now we're going to keep it a bit simple, and we're going to introduce a new symbol which we call the node error associated with the jade node. So we're going to just define it for now to be this error, which we're going to take a look at later on. So delta is the derivative of my error with respect to this jade node, right? And we're going to denote it with delta j. So delta j is this node error, and it's an error that we place at the jade node. So then it means that my derivative with respect to wji is given by this node error times delta aj delta wji. So again, looking at these terms, this is what we are set out to compute. So we want to update our model parameters wji. For that, I'm going to need the error with respect to my jade activation. So I'm going to, for now, let's call this thing delta j, the node error. And then, of course, we need the derivative of the node aj with respect to wji. Okay, so let's focus on that one first. So this is what we just did. So we said we want to compute this error, and it's going to be given by delta j to delta aj delta wji. And now we want to compute this particular term. So before I proceed, I just want to mention that I'm not going to write out all these layer indices all the time. And I'm going to use the index notation to refer to the layer. So whenever I'm talking about, my final layer in this particular chain that I'm considering, I'm going to use the index k. So all nodes in this layer will be indexed with the index k. And then if I talk about the layer before this, I'm going to use indices j, and the layer before this, so let's say layer -2, is going to be referred to with index I. So whenever I write zi, this means this is a hidden unit corresponding to a layer L-2. So we have this ordering I, j, k going from layer -2 to -1 to my current layer. Okay, so with that said, this hidden unit is based on the activation J, which is obtained via linear combinations. So I sum over I, the index in the previous layer, W, J, I, the hidden units of that layer. Okay, so of this thing, I now need to compute the derivative with respect to W, J, I, and it immediately follows that, well, it's going to be Zi, right? So the derivative delta Aj to delta Wji is given by Zi. Okay, that's simple enough. Okay, so then this is what we currently have. That my error, my derivative with respect to Wji of my error function is given by delta j, so the node error j times Zi. Okay, and now we're going to focus on this particular term, which we call the node error. So now we are going to actually compute this derivative. And to do this, recall that my final error is going to be determined via these nodes. And these nodes are again a function of the aj, of the node of which I'm now currently computing this derivative. So if I make this a bit more explicit, I'm going to say that my error function, it depends on these nodes ak, so the nodes in this layer, and these nodes in turn depend on this jade activation, right? So each node contributes to the error, and each of these nodes in turn are a function of the aj that I'm currently considering. So now I can compute the multi-dimensional chain rule. So in order to compute this, I'm going to use the multi-dimensional chain rule, which tells me that this derivative is given by sum over k, so all the parameters that depend on my jade activation. So I'm sum over all these parameters ak, the derivative delta e with respect to this parameter, delta e delta ak, times the derivative of this particular parameter to aj. So this is just applying the multi-dimensional chain rule. And of course, these derivatives are maybe also hard to compute, right? So maybe we have downstream, we have more intricate relations, which I'm not going to focus on at the moment. So again, for now, I'm just going to say, I'm going to call this thing delta k. So the node errors at these nodes ak, at these activations ak. Okay, so to keep it a bit simple, I'm going to denote this as the sum over k, my node errors k times delta a k delta a j. So the derivative of my kth node to the jade activation. So this tells me if I want to compute the error at node j, then I'm going to need the errors at the nodes at my higher layer in the network, right? So we're going to have this flow of information that the error at my higher nodes are going to contribute to the error of my lower nodes. So this is essentially the idea behind backpropagation. But just for clarity, I'm going to write out that indeed each hidden unit, let's say the Zj, is obtained by applying this activation h to aj, right? And the same for my y case, it's obtained from my kth activation in that particular layer. Okay, so we are going to leave these node errors for now for what they are, and now we're going to focus on this derivative. Okay, so this is what we had so far. We were computing the derivative of my error with respect to wji, and this consisted of the node error, the jade node error, times zi. And we were currently focusing on computing this particular term, and we saw that this particular term was obtained via a combination of my, let's say, upstream node errors delta k. But in order to make this assignment, we need to compute the derivative delta ak to delta aj. So let's now just compute this thing. And recall that my AK, so my Kate activation, is obtained as a linear combination from the nodes at the lower layers, right? So the hidden units. Okay, so let's just insert that. So these ZJs are directly obtained. So let me just write it out. So each ZJ was indeed obtained by applying this activation unit, right? So let's just fill this in. We're going to compute the derivative delta AJ of this sum over J WKJ, and then apply this activation function to my Jade activation. And this derivative directly follows from the chain rule, and it's given by WKJ times derivative of this activation function with respect to its input, evaluated at AJ. Okay, so that's simple enough. We compute the derivative of AK to AJ, and that's given as follows. So my weight WKJ times the derivative of my activation function. And this is something that you can predetermine before you start making all this computation. I'm going to give some simple examples of what the derivative of activation functions look like. But now I have a way of computing these delta J, so the node errors, the Jade node errors, simply by taking computing derivative of my activation function at node J times the sum over K of the node errors at the higher layers. So really I'm just filling in this formula, right? So we just computed delta AK, delta AJ, and that gives me this expression in the end. So this clearly shows if I know the node errors at these higher layers, so delta K, delta 1, then I can obtain my node error at the node J simply via this update rule. So we have a flow of information, the flow of errors from the higher layers to the lower layers by multiplying each error with the corresponding weight. So we have these higher node errors, which are multiplied by this weight WKI, and that together with the derivative of my activation function gives me the error at node J. Okay, so this is something that we can actually compute, right? Because all these activations, we can compute them in the forward pass. These WKJs, we know their values, and we also know how to take the derivative of my activation function. It's just filling this in, and that gives me the delta J. The only starting point is actually computing the derivative at my very last layers. And that's what I'm going to show in the next slides, how to do this. It's actually quite simple. So once you know the node errors at the last layers, we can propagate these errors all the way down via this particular rule. Okay, so then this update scheme, so the scheme for computing these derivatives has a very clear structure to it, right? So we have this forward pass, and in this forward pass we propagate the information from the input all the way to the last layer using just the definition of our network. So each node at AJ is obtained from the activation from the lower layers by this linear transformation where each node at the previous layer was activated by the activation function, right? So this sum over I. So this really is how we define the network to be. The activations at this layer are obtained via linear combinations of my hidden units at the previous layer. Okay, and once I've performed this forward pass, I also know the node values at my output, right? And these node values then determine the error. This also means that now I can start computing the derivatives of my nodes, of my error with respect to these nodes. Specifically, you would start with computing the derivative, the node error delta K. So at the output, I made these errors, and these errors were defined to be the derivative of my error function with respect to this particular node. And because my outputs directly determine the error, we can simply compute this, which in the least squares error, for example, boils down to yk minus tk. Right? Suppose my error was given by the sum of squared errors, or the squared error tk squared. Then the derivative of this thing would give me this. So I have a way of computing the errors at my output nodes. Okay, and then we also just derived a way for computing the derivative at the lower layer nodes via this update rule. So, okay, so now we can propagate these errors down to the lower layers via this update rule. So the derivative of my activation at node j, and then the weighted sum of all my higher layered errors weighted with my model parameters. Now I put this remark down here because we have to, of course, be careful with skip connections. So we could have models that directly propagate information from here to here. Then, of course, we have to check for the links that contribute to this activation. So that means I'm summing essentially over all nodes upstream that are connected to the node that I'm currently updating. It's just something to take into account. Okay, so that's essentially the backpropagation phase. So in the backpropagation phase, I propagate errors from the end all the way down to the lower layers. And then if I'm done with this backpropagation, I also know what the derivative with respect to the model parameters wji are, and that's simply given, that's one of the first things we derived. It's simply given by this node error delta j times zi. And these derivatives can then in turn be used in your whatever optimization scheme that you use, but almost any optimization scheme relies on this derivative. And now let's just take a look at the gradient descent algorithm, what it does. We update the node parameter wji. So at my next iterate is going to be the parameter that I already had, and then I walk in the negative gradient direction, which was given by delta j times zi. Okay, so really this summarizes everything. So in the forward pass, I make sure that all my activations are computed, and then I can start the backward pass, and that is start off by first computing the error at my output nodes, and then I backpropagate these errors to obtain also my node errors at the lower layers. Now, when I'm done with that, I not only have all the activations, I also have the node errors, and then I can start computing the derivatives simply by taking the product of my node errors with the actual hidden activations. And this in turn can be used to update my weights in an iterative update scheme. Okay, now I'm going to end this video with some examples. So depending on your error function, maybe your errors may look slightly different. But we already saw actually for a particular class of activations and targets that we optimize, we always end up with this very simple form of the node error at the outputs. For example, if we consider logistic regression, then we typically minimize this least squares error function, and the derivative of this error function with respect to y is simply given by this difference. So this is the error that my target makes with respect to the target. So the error that my prediction makes with respect to the target. And a similar thing happens if we consider classification, and we use as error function the cross entropy loss. We computed this in the previous videos. We computed the derivative of the logistic sigmoid, which is the two-class version of this thing. And then we saw that we end up with a very similar error. All right, so that's simple enough, and these are then the errors that we use to start off our backpropagation. Now a final note on which kind of activation functions you could use and what this would look like. This is an example. Let's consider this two-layer neural network. So a two-layer neural network which maps an input to some k-dimensional output vector by passing it through one hidden unit layer directly to the output. And let's consider the regression problem. So I'm not going to apply an output activation to my outputs, but as for the hidden units, they will be computed by the tan(h), the hyperbolic tangent. So my activation function will be the tan(h). Now this tangent hyperbolic is given as follows, and it has a very nice derivative. So this is what I'm dealing with. So this is my activation function. And it has the following derivative. So this derivative, we need this when we apply our backpropagation, right? and we talk about regression. So we have this quadratic error function, and we just saw that if we compute the derivative of this error function with respect to node yk, then it's just simply given by the difference between my prediction and the target. So I have my node errors at the output node, so now I can start backpropagation. And recall that the backpropagation, so the backpropagation rule was given by, well, the fact that I need the node errors at the last layer, so that's what I have. I also have the current weights, but I also need to compute the derivative of my activation function. So let's just fill this in. So the derivative of the tangent h is this thing, 1 minus the hidden unit squared, so 1 minus the hidden unit squared, and then times the rest of it. So this is really my update rule, which I'm going to use to propagate the delta case down to the lower layers. So step 1 is this forward propagation, then step 2, compute these node errors and propagate them backward via this backpropagation to obtain the node errors at the lower nodes. And since we're now considering a 2-layer neural network, I only need to compute these nodes at this layer, right? Because I do not have any weights at this point, so I do not need any node errors at this point. Right, so once I've computed all these delta j's, I'm essentially done with my backpropagation, and then I can simply compute the derivatives of my error functions with respect to my model parameters via this update rule, which was given by the node error times the node of this previous layer. And that's explicitly given as follows. Okay, so that wraps it up for error backpropagation. So this entire scheme summarizes how to compute your gradients in the end. I would recommend just take your time, go over this example after the video, but whenever you have to implement this, or whenever you need to know how to compute the gradients, just follow this scheme. We have a forward pass, moving all information forward. That allows me to compute all the activations in my neural networks. Then I need to compute the error that I make at the output, and I can propagate it backwards via this simple update rule. And that in the end gives me an expression for the derivatives, which in turn can be used to update my weights, for example, via a stochastic gradient descent. So far, we have covered supervised learning methods in the context of regression and classification. We now move on to the class of unsupervised machine learning methods. So this is what we've been dealing with in the supervised setting, right? So far, we've always worked with data of the form input-output pairs. So we have a set of measurements X and the corresponding targets. And now we want to come up with either predictive distributions, like given a new data point X, what is the probability of observing a corresponding target T? Or we approach it from a discriminative setting, let's say a non-probabilistic setting, and where we just want to model the relation input to output. And we just model that by recovering some function f that performs this task. And then we subdivided this class of supervised learning methods into regression and classification problems, where in the regression setting, my targets took on continuous values, so any value on the real line. So that was a regression problem. But we also considered classification problems where the target could only take on one out of a specific set of values. And this target represents maybe a class. And now in the upcoming videos, we move towards unsupervised machine learning, where we have all this dataset of observations X, but without a clear target which we want to recover. And now our goal is to do something useful with this data. We want to uncover the structure of the data, or maybe we want to infer maybe hidden class labels. Maybe there are targets which we do not observe, but which we know there should be such targets. And a first goal could be, for example, density estimation, where we simply want to reconstruct the probability density that generated this data set. This could, for example, be useful for outlier detection. Suppose I now observe a new X and I want to know well, the probability of observing this X, and if it's highly improbable, then maybe it's an outlier and there's something wrong with your detection system. I don't know. Could be anything, but we could also use this probability to generate new data points in a simulated environment, for example. But maybe more interestingly, and that is what we're going to focus on in the upcoming videos, is the notion of a latent variable. And this latent variable z, so let me denote this, let z be a latent variable that influences how we observe x. And that's actually better represented by this probability distribution over there, this conditional probability. And the idea is as follows. So suppose I have this whole data set of, let's say, real estate related measurements. So things like house prices, the size of the property, the size of the garden. Those are all measurements related to a house on the real estate market. And so we have all these measurements stacked in this data set X. And maybe now we want to infer some structure of this data, because you can imagine that maybe some of these values are highly determined by maybe the city in which the property is located. Some cities, they have bigger houses and more expensive houses, and some cities only have tiny houses, I don't know. So we want to recover the structure such that maybe in downstream tasks we can rely on this structure for making particular decisions. So we then call this unobserved variable z, this latent variable, it is unobserved, but we sort of assume and maybe even know that there is such a latent variable. There is such thing as a city which influences all these measurements. And now the task could be maybe to recover this kind of structure, recover the different cities that there are. Now, such problems would relate to clustering. So clustering my data points based on this latent variable. And in this case, the latent variable would be, for example, the city. But we can also use unsupervised learning for dimensionality reduction. Suppose I have this whole set of measurements like house price, property size, garden size, a lot more, and maybe they can be reduced to one or a few values. For example, maybe just knowing the property size tells me a lot about the actual house price and the garden size and stuff like that. So that's also going to be part of unsupervised learning, is sort of uncover this structure that govern my data such that I can deal with less parameters in the end. Now in the upcoming videos we're going to talk a lot about latent variables, so it will become more clear very soon. But this is roughly the idea behind it. We have this observed variable x, and that's the data basically. So we have all these x's, but we also have unobserved latent variables that influence how my x's came to be. And that is graphically depicted over here, and in formulas it's constructed as follows. So we assume that there's such a structure of a latent variable influencing my x. So my final probability of observing x is determined via this adjoint of observing x with this hidden or latent variable, which we do not know, but we can marginalize out this z once we have this joint to obtain my probability for x. Okay, so that's how we do this. We assume there is such a latent variable, and therefore there's such a joint probability distribution. And that also means that we can make this factorization, right? So this joint is given by the conditional of x given my latent variable times the prior or the probability for z in itself. Suppose I'm given such a latent variable, then this tells me a lot about what kind of values for x I can expect. And if I have a different latent variable, I have a different distribution for x. So we have this latent variable conditional distributions. And then of course, in order to reconstruct this joint, I also am going to need a prior or some probability for this latent variable in itself. Okay, so that's the continuous situation, and the same for the discrete setting, right? So when I talked about predicting these house prices based on the cities, now z could be my discrete latent variable. It could be city number 1, city number 2, etc. And then my overall probability for making a prediction for a particular house price can then be obtained by summing the probabilities for a particular house price x, for example, summing over all the probabilities in all the cities, essentially. I hope this example somewhat makes sense, but maybe we just move on to another example. I talked about this clustering, like uncovering the structure of my data, and suppose all these points over here are all different measurements. Let's go to a different example. Let's say these measurements represent, we're observing animals, and these x's represent, for example, the height of the animal and the weight. something like that. So we see this correlation when we observe bigger animals. We also observe higher weights, and then we make this assumption that we're measuring actually. Maybe we make this assumption because we look at this data and we see roughly 2 clusters. So it's a bit dense over here and here, and there seems to be a separation here. So now we can maybe assume that we're actually dealing with 2 types of animals. So that would be my latent variable. For example, the latent variable could be, I don't know, animal type. And I said the horizontal axis was height. The vertical axis was weight. So then once we make this assumption that there is a latent variable, namely the animal type, that influences my observations, then maybe it becomes more easier to actually model this distribution that generated all these data points. Meaning that I'm going to assume that the probability for a particular observation X is going to be given via the marginalization over this joint Px and my latent variable, where I made this factorization of a probability of X given my animal type times the probability of observing that animal type in the first place. So suppose my latent variables are cats and dogs. I'm only measuring cats and dogs. Then suppose I'm measuring a dog. Then maybe I assume the probabilities of observing a particular weight, width and height is given as follows. So dogs are typically heavier than cats, for example. So assume maybe a width and a height somewhere around this point, and then of course we have some spread around this. One dog is larger than the other. And so maybe there's such a distribution for cats as well. So let me draw that. So let's say the average cat has some height and weight corresponding to a point over here, and then there's some spread around it. Like not every cat is the same. So then we have identified 2 distributions in our latent variable modeling approach, where the first one corresponds to the probability for my width and my weight and height measurements, given that I'm observing a dog. And with the other density, I'm modeling basically the width and height, given that I'm observing a cat. So now I split the problem into modeling 2 separate distributions, which are separately easier to model, but they still give me the information that I'm after, namely the probability for making an observation X. So via this marginalization process, by marginalizing over, cats and dogs, essentially. And then via this marginalization, I would be able to recover the probability distribution for the data that I just observed. Okay, so that's essentially the idea about unsupervised learning with latent variable models. So we assume that there is such a latent variable that influences how my data is generated, and now I'm going to use this to apply structure to my modeling approach and to my data essentially. And in this case, you could think of it as a clustering approach, because we sort of group all these points together with one latent variable model and cluster the other points with another model. And now this also means with such a probabilistic interpretation that maybe I can, given a new data point X, I can try to infer which latent variable class it would belong to. And because now this point has a higher probability in the conditional class for cats, I can probably tell that this data point belongs to the measurement of a cat. Okay, and then we can also use this idea of latent variable modeling for dimensionality reduction. For example, in this right figure, suppose I have all these 2D measurements, so all these points over here. We see that in this case, they are nicely concentrated along this red curve. So what I'm actually looking at is actually a one-dimensional manifold or one-dimensional data structure, where my latent variable could, for example, encode for a particular point along this line. And that would actually then tell me also, what my observation in terms of these 2D data points would be. And that will be the main idea about working with continuous latent variables, to use it for dimensionality reduction and sort of to recover the underlying structure of my data with, well, continuous latent variables. And this will be covered in the next lecture, so in the video series numbered with 10. But today, in the upcoming videos, we're going to focus on discrete latent variable models. And we're going to start off with clustering in this non-probabilistic setting, so really focus on a classical k-means clustering algorithm, and later we move to a probabilistic setting, which more closely models what we just discussed in this example. Clustering falls in the category of unsupervised learning methods, where we are set out to learn the structure of the data in terms of a discrete set of clusters. Now today we cover one of the most famous methods for clustering, namely k-means clustering. Now remember, we're talking about unsupervised learning, so we're considering data points without targets, so just observation X, and that could be visualized as follows. Suppose we have these 2D measurements, which results in this green point clouds. Now what we're going to assume is, we're going to assume that there's a discrete latent variable, and this latent variable encodes for the cluster or the latent class, which we do not observe, but we sort of assume that there is some latent variable that results in the fact that we are observing my data points in two clusters roughly. And now we're set out to recover this latent variable. Now let's put it like this. All our observations X are drawn from this probability distribution for X. So when I make an observation, sometimes it lies over here, sometimes it lies over here. But generally we tend to see these two clusters. So we're going to assume that there will be two clusters, a discrete latent variable which can take on two values. And let's denote it as follows. So we have a latent variable Z, which either means it came from the blue class or it came from the red class. Then basically this means that my data point is either drawn from this conditional X given, I'm considering the red class, or we say my data point came from my blue class. So then I have this conditional X given my blue class, where points drawn from this blue class are most likely to occur around this blue cluster center. That's sort of the latent variable approach that we consider here. Now in this k-means clustering approach, we're actually going to discard the idea of probability. So we're not going to talk about these probabilities. We're just going to perform this clustering, but we can still talk about clusters as being latent variables, right? So these latent clusters that are responsible for particular sets of data points. So now we're going to let go of this probabilistic interpretation, and for now not talk about probability distribution, but we're going to make hard assignments. We're going to say that this point either belongs to this blue latent class or it belongs to the red latent class. But our original dataset in itself doesn't have this latent variable information, right? We're only observing these X's, and that's why we call it this green. So we do not encode for classes at this point. But once we have done our clustering, then we can look for new data points and make a hard assignment for the latent variable blue versus red. And we're going to do this via the k-means clustering algorithm, which is based on the fact that each cluster has its own mean. So the cross over here is called, let's say the mean for cluster 1, and then this cross is going to be the mean for cluster 2. And then whenever a new data point comes in, this X for example, we're going to check which mean is closest, and then we simply assign a point to that class. Alright, so that is what we're going to do. And then the k-means clustering algorithm works as follows. We can formulate it as a minimization problem. So what we're dealing with is all this data set of observations xn, and we're going to cluster them. So those are those green points. And we're going to cluster them into two groups, for example, or let's say in k clusters. Now we can do this by minimizing the following error function or loss function. And now this error will be a function of my cluster means and the labels that I assign to each data point. So each point is going to belong to one of the clusters that's encoded via these latent variable assignments Z and K, where each Z and K, so for each data point n,
I consider k classes, and this value is either 0 or 1. And that leads to a sort of one-hot encoding of my latent variable classes. Meaning that my latent variable set and k looks like this. So my end latent variable looks like set n1, set n2, up to set nk. And this vector consists of zeros and ones, where it is only one for the class to which it is assigned to, right? So it's a one-hot encoding of the kth class. Okay, so that's what we're going to do. We're going to assign each data point to one of the classes via this one-hot encoding of my latent variable. And I'm going to do that in such a way that my total error is going to be minimized. So that means for a fixed k, for a fixed cluster k, I'm going to pick a mean. And then for all points in this cluster, I'm going to sum over the square distance from this point to this mean, right? Because this thing is only 1 if, if the kth index is indeed 1. So I'm only summing the errors within one cluster. So going back to this example, suppose I have a cluster mean mu is 1, then I look for all points which are assigned to cluster 1, and then I want this mean value to be placed at such a place such that the distance of all points to this cluster mean is as small as possible. But this also works the other way around. Suppose I have fixed a certain mean, then I want to assign the points to the closest mean, because by making this assignment to the closest mean, I'm also going to minimize this loss function. So I have two things that I'm going to change, the means and the assignments, and this leads to an iterative optimization scheme called k-means clustering, which is as follows. So we are going to initialize the cluster means mu k with some random initialization. So this was my green data set, and then I'm going to consider two classes. So I randomly place these two cluster centers over here. So that's step 1, this initialization. Then I'm going to iterate the following. First of all, I'm going to make an assignment of each point to the closest cluster mean. So that's essentially stated here formally, right? For each xn, I'm going to select the cluster. So I'm going to take the minimal cluster, or the cluster that minimizes the distance, and that will be the cluster to which I assign this point to. So that looks like this. So I have this cluster points initialized like this, and these blue points are all closest to this one, and the red points are closest to this one. So this is the assignment step, which we are going to label as the E step. I will explain in a minute why we call it the E step. So this will be the E step, the assignment step. And then once we make this assignment, we're going to update the means. So that's denoted with the M step, simply by taking the average over all my data points within a class. Remember that the set and case is only 1 for this data point when it corresponds to the kth class. So I'm really summing only for a fixed k, I'm summing only for the points within that class and average over it. So now I'm updating my cluster means. Okay, so this update step will be denoted with an M, the maximization step, and this leads to a new set of cluster means, right? So we have all these blue data points, we have slightly more blue points on this side than on this side, so my mean is somewhere over here. So that's what you see over here, and the same for the red, it's heavier on this side, so the mean over all my red points is going to be located over here. And now, once I've done that, I again go to perform this E step, or also the assignment step, and that gives me this new distribution of points. Now all points closest to blue to this cross will be marked as blue, and all points closest to the other cross will be marked as red. Okay, now we're going to iterate this. So once we updated our assignments, we're going to update again the cluster means. So that's the maximization step, the M step, and that gives me a new set of means mu k. And again, we update our assignments by assigning each point to the closest cluster mean. Then we again update our cluster means. Then we again make this assignment, and so on. And we keep doing this until convergence. So at some point, the cluster means will not change anymore. So you see that this solution is exactly the same as this solution. So we reached convergence and we're done with the clustering algorithm. Okay, so this is a very simple algorithm consisting of an E step and an M step. And we call this this is a sort of instantiation of the expectation maximization algorithm. So we call this the expectation step. And we call this the maximization step. And for now it is a bit artificial to call it the expectation and maximization step, but later on we will consider a probabilistic version of k-means clustering, in which this expectation has a particular mean and the maximization step also has a particular meaning. But for now, let's just use it as labels. So we have an E step in which we update the assignments of each point to the corresponding cluster, and we have an M step which is used to find the new cluster means. And that describes this very simple algorithm where we have this assignment step, followed by an update or maximization step, update of the means, and we iterate this. And the nice thing about this algorithm is that with every step, so both with the expectation step, with the E step or the assignment step, as well as with the M step, we reduce this error function that I defined before. And it keeps reducing until it reached convergence. I'd recall that our objective J is defined as J is the sum over all my data points, sum over all my clusters, Z n k times the distance of my n data point to this particular cluster mean. So that was what my objective was defined to be. And then we have this assignment step. And by definition of this assignment step, for each xm, we're going to select the label set n such that this thing is minimized. So really by definition of this assignment, we're going to make a decrease in this loss function. Okay, so that's essentially this assignment step. And once we've made this assignment, we're going to update the cluster means. And then again, this results in a decrease in this loss function because we're going to choose the means mu k such that this error is minimized within that cluster. And I'm going to show this in the next slides actually, that this maximization step or this M step really reduces this cost function j. But essentially what is happening here, that after this M step, the majority of points within this cluster will get closer to the cluster mean. Okay, so we iteratively keep increasing this loss function until it converged. So we're actually able to show that the k-means clustering algorithm will converge, but it actually is going to converge to a local minimum, because as a function of both mu k and z and k, so these cluster means and the cluster labels together, this loss function is highly non-convex. And this property of convergence to a local minimum is actually obtained by fixing a particular mu and then updating z and k, and then fixing z and k, and then update the mu k, so this M step. So once this is fixed, this will become a quadratic loss as a function of mu k, and hence a convex optimization problem. So each of these individual steps solves some convex optimization problem, but when we treat this loss as mu k and z and k together, we're dealing with a non-convex problem, which means that depending on my initialization, depending on where I place these points, I may end up with different partitionings in the end. Okay, so this tells us that this k-means clustering will find a local minimum, but it is not guaranteed to find the global minimum assignment of points and cluster means. And so the best thing that we can do is really work with random restarts. So we start with different initializations, and then we let the algorithm converge. We do this multiple times, and in the end just select the clusters, which really minimizes j over all these random restarts that I did. So that's the best thing we can do, just run this multiple times, and in the end select a solution that really has the lowest value for j. Now what I'd like to show next is that this M step actually really minimizes this j, so we can derive this step by fixing my class labels or my assignments, and then finding the mu k that really minimizes this convex optimization problem. And the approach that we've been taking so far a lot of times is taking the derivative of this loss with respect to mu k. This is the parameter that we're going to update, and set it to 0. So what would the derivative of this quadratic function be in terms of mu k? Now, first of all, we know that this L is a class index, right? So this mu L. So this derivative only does something whenever L is the same as K, meaning that this derivative is only non-zero only when L is K, and hence this sum disappears and we can just fill in the K over here, because that's the only case where the derivative does actually do something. And then of course we can pull this derivative inside the sum, right? Because this sum in itself doesn't depend on K. Okay, that's step one. And then the derivative of this quadratic form, we also computed that before. So what we're actually doing here is computing the mu K of xn minus mu K transpose xn minus mu K. And this will be equal to minus 2 times xn minus mu K transpose. Okay, so this is derivative and we set it to 0, and now we're going to solve it with respect to the cluster means mu K. So that's what we're doing in this bottom part. So we take the transpose on both sides. So actually we just get rid of this transpose essentially. We're going to split this sum, and then we move this part, which depends on mu K, to the other side. So solving this tells me that the most optimal cluster mean values are obtained simply by taking the average over my cluster points of my data points within this cluster. Because recall that these Z and K's only take on the value 1 whenever my data, my end data point belongs to the Kth class. So really I'm summing over my data points within this class, and then I normalize by the number of points within this class. So really this is taking the average over my points in this cluster. So that explains that with this M step, we're really minimizing our objective function here. So in that sense, maybe this M step can be interpreted as a minimization step, but we call it a maximization step because when we move to the probabilistic setting, this M step actually solves the maximum likelihood of my probability distribution. But that's something that we discuss in the upcoming video. For now, it's clear to know that the k-means clustering algorithm minimizes this objective J step by step both in the expectation step as well as in the M step, in this case a minimization step. Okay, now let's go over some applications of k-means clustering. In this first example, we're going to use it for image compression, and this is an example from the book of Bishop. And maybe it is a somewhat old-fashioned or naive way for image compression, but it will get us started on, well, what kind of applications can be solved with k-means clustering. Now, the idea is here to represent this image with as little data as possible. And we're considering the following problem. So we have data points, which will be our clusters. So the xn's, each xn is 1 pixel, and this 1 pixel has an R, G, and a B value. So those are my pixel values. Now, instead of storing all these pixel values of all these RGB values, I'm only going to store the cluster to which each point belongs to. So this point belongs to the blue class and this one to the yellow class. And then with this information, I can reconstruct such an image. But if I consider, let's say, 3 different colors, then this would be a representation that I can store cheaply. And if I use 10 colors, basically I'm saying I want to represent this image with only 10 colors, and I'm going to store for each pixel which class color this belongs to. Right, so we're going to cluster all these color pixels into K clusters, where each cluster represents is a color representation. Okay, so that's what we're doing. We're just throwing all these color pixels into one big pile, and then we recognize that there are a lot of colors that are similar. So we're just going to we're going to cluster all these colors that are similar together. We call them yellow, for example, and all these points are similar. We call them blue, and this allows us to compress the data, because now I only have to store, let's say, I have all these pixel values. I only have to store, let's say this pixel belongs to class 1, this to 2, this to class 1, etc. So I only have to store these integer values at all these pixel locations. So suppose my image contains x by y pixels. Then now I only have to store x times y integers, which represents the classes. So these are either 1 or 2, for example, in this 2 class case. Whereas in the original image, I would have to store all these RGB values. So RGB for one pixel, RGB for the other pixel, yeah, etc. So that would mean I would have to store x times y times 3 of such values, but also now my values, so this number of values in the range 0 to 255. So I have much more data to store. Okay, again, so this is maybe a bit naive way for image compression. There are way better methods than this, but the idea is there, right? So we can use clustering also for compression, and maybe also now in this image segmentation or analysis task also for segmentation, because now pixels that are of similar color, they are clustered together. So we have sort of the segmentation of, let's say, blue and yellow. Of course, a bit silly method for segmentation because it doesn't take any spatial relations into account, right? Just similarities between colors. Okay, enough for about image compression. There are also some limitations of k-means clustering. And one of the main limitation is that k-means clustering only generates spherical clusters. So let's write it down, only generates spherical clusters. And this has to do with the fact that my clustering is based on distances of points to my cluster centers based on the Euclidean distance. And then, well, all points with equal distance to my cluster, that forms a sphere, right? So with these kind of complex half-moon data sets, you will never make a proper clustering with k-means clustering. Another limitation of k-means clustering is that each cluster has the same size. So let me write it down. Each cluster is of equal size, and that's in this mouse data set. So this is sort of a Mickey Mouse kind of figure. So we have a face and 2 ears over here. Ideally, we want to cluster these ears separately. And if you work with 3 classes, again, because we use this same Euclidean distance for each class, we end up with clusters of about equal size. And of course, we can increase the number of clusters. This sort of solves the problem because now each cluster is of about equal size, and then these ears can be separated, and then I would just still need a way to cluster the face using these 3 separate clusters. But that could be considered a limitation of k-means clustering, right? That each cluster is assumed to be of equal size, and whereas in practice, in most datasets, this will not be the case, and we will come up with a solution to this in our probabilistic framework, actually. Now we can come up with some interesting points of improvements for k-means clustering. First of all, recall that this error function that we minimize, so this j, is actually a sum over all my data points and the sum over all my clusters of z and k, and then the Euclidean distance of xn to my cluster mean, my kth cluster mean. And so this is an error function which decomposes into a sum of individual errors that I make. So this also again makes it a candidate for stochastic gradient descent for minimizing this particular thing. So that's nice. So also for this k-means clustering, we can apply stochastic gradient descent to minimize j, for example, to update our cluster means. So that gives me the following update rule. And in that way, I can come up with a very efficient algorithm that only considered one data point at a time. Now, one issue that I pointed out in the previous slide is that this k-means clustering is based on the Euclidean distance of a point to the cluster mean. And so what we could also do is consider other type of distances between points, and this actually results to what is known to be the k-medoids algorithm. So it follows the same structure as the k-means cluster, but now my Euclidean distance can be replaced by any other dissimilarity measure or distance between my points xn and clusters mu k. And in this way we can also introduce distances that are less sensitive to outliers. Maybe you recall from previous videos that this least squares minimization problem is highly sensitive to outliers, especially in the classification case where I'm dealing with discrete data. Maybe also when my data isn't nicely Euclidean, I can introduce different type of distance metrics essentially. Okay, so in summary, the k-means clustering algorithm, it is a very famous algorithm and it's widely used primarily because it is so simple to implement and it is a very fast algorithm. But it also suffers from some problems, right? First of all, we saw that it only converges to local minima, so it does not provide a global optimal partitioning of my data. We saw that the clusters that arise from k-means clustering, they are sort of spherical, right, because of this Euclidean distance. And also the k-means clustering algorithm is sensitive to the scales of features. And with that I mean the following. Suppose my data looks like this. So I have, let's say, a two-dimensional data set of points which are maybe stretched in one direction, so this distribution, and we have another set of points stretched in the along also the same direction. Then ideally you would want to cluster this into these elongated clusters, right? But what's happening with k-means clustering is, again, that we assume a Euclidean distance. So we draw these circular clusters at these points. Still, they would be able to find this division between the data sets, but you can imagine that maybe this algorithm is sensitive to changes along this direction compared to this direction. Now, ideally, you want your clustering algorithm to take this anisotropic distance into account, or alternatively, we can pre-process our data to make it isotropic. And that's something that we will learn in the lecture 10. When we talk about principal component analysis, we will introduce a widening operator, which turns this data set into, isotropic point clouds. So we can turn this into isotropic features via a widening operator, and that makes it actually the data more suitable to work with k-means clustering. Another limitation of k-means clustering is that we have to choose the number of clusters in advance. So this requires some pre-knowledge from us. So like, okay, I'm going to assume that there's k latent clusters in my data sets. Maybe because someone told me so, or maybe I inspected the data and I roughly saw 2 point clouds. Okay, but then there's also a lot of heuristics for automatically determine the right amount of clusters k, which we're not going to cover in this course actually. And then finally, and this is what we're going to solve in the upcoming videos, is that now the cluster assignments are hard. And if you have overlap between the distributions, then maybe you're not fully sure whether a point belongs either to the red class or to the blue class. And we can deal with this via a probabilistic modeling approach. And that's what we're going to discuss next using Gaussian mixture models. Before I proceed to Gaussian mixture models, I'd like to briefly go over the method of Lagrange multipliers for solving constraint optimization problems. In the upcoming video, we will be optimizing Gaussian mixture models, and this involves a constraint optimization step. Moreover, later on in this course, we will again encounter constraint optimization problems, which we will solve via the method of Lagrange multipliers. So it's worthwhile to take a moment and go over this method. Now, the setting is that we're set out to find the maximum location of this function f. So f is the function that we're maximizing, but we're doing this subject to a constraint, which we're going to denote as follows. And this is maybe abstractly put, but what you look at here, we say that my point x should lie on this level set, right? This g of x equals c represents a level set. So all the values that take some constant value, that's actually denoted over here. But maybe let's make this a bit concrete. So my g of x could be, for example, the function that takes the length of my vector x, and we want this to be equal to some number. So we're looking for points x which have a particular length. This could be a constraint, right? So this g of x can be thought of as this function that spits out the length for each possible x. So this really is a function, and setting it equal to c creates this level set of points that indeed all have the same length.
All right, maybe we could make this a bit more visual. So let's say, so I'm now plotting my function g of x as some density, right? So that's how I'm going to plot this. So give me a moment to draw this. Okay, so this gray region could represent my function, my constraint function g of x. So maybe darker means a higher value or a lower value. But the idea is that then when we fix some c, we select all points which have the same value, right? So that creates this level set. So this level set then defines the points of x, the points x that satisfy this constraint. So we want our solution to lie somewhere on this red level set encoded via my, well, constraint g of x is c. Okay, so that's the constraint, but then we're mainly interested in finding the maximum of this particular function f of x. So let me also make a drawing of this. Okay, so suppose this orange-red region is the function that we want to maximize, and it has its maximum over here at this point. So darker means higher values. So actually my optimal location would be at this point, but now I am optimizing under this constraint, so I actually only am allowed to pick points on this red curve. Okay, and now the Lagrange multiplier method provides me a way of finding this point which really takes on the maximum value of this f of x, but still lies on this constraint on this level set. And the idea is as follows. First of all, we note that this useful property that the gradient of g of x, the gradient of this function that defines my constraint, is always perpendicular to, well, this constraint level set. That's really a property of level sets. So that's also nicely discussed in the appendix E of the Book of Bishop. Actually, this entire Lagrange multiply method can be found also in that chapter. But what it says really is that if I take the gradient of g, so this would be the gradient of g, it always is perpendicular to this level set. So wherever I look on this level set, the gradient of g is perpendicular to it. Then another important observation to make is that at this constraint maximum, the gradient of f, so the function that we want to maximize, this gradient should also point perpendicular to this constraint surface. Because if I, for example, consider this point, the gradient of f points in this direction, so this would be the gradient of f, and this actually means that I still have a component of this vector along this level set, right? Because if we want to optimize f, so now we're talking about optimizing, so this can be done via gradient ascent, so we walk uphill towards the maximum. So actually I want to move along this gradient, and now the problem is constrained, so I cannot make the step directly in this gradient direction, but I could only move along my level set, along my constraint. And since this gradient still has a component in this direction, so I could actually move in this direction, and that would optimize my function f. So as long as this gradient isn't perpendicular to, well, the gradient of g, I am still able to move into a direction that optimizes f. So suppose you do that, then at this point the gradient again points in some direction which isn't fully perpendicular to my level set, so it allows me to move a bit in this direction. And at some point, really when there's no improvement anymore to make, then the gradient both of f and the gradient of my constraint, they are either parallel or anti-parallel. Okay, so this tells us that at a constraint maximum, the gradient of f should also be perpendicular to the constraint surface. Otherwise, I would still have a component of this gradient which isn't fully perpendicular to my level set, and that would allow me to, well, update my point x a little bit in the right direction. But when they are both perpendicular, then, well, I cannot further improve my function values anymore. Okay, so this means that at such an optimal location, the gradient of f and the gradient of g are either parallel or anti-parallel, but it doesn't mean that they have to be the same, right? They can point in different directions and they can have different lengths.
but it essentially means that there exists such a value lambda such that the sum of these two gradients equals 0. And this lambda value will be called the Lagrange multiplier. So with that said, we basically are saying that at such an optimal location x, we need to satisfy this constraint for some optimal value lambda, which we're not sure yet what this value is, but there exists such a lambda such that this constraint is satisfied. And now it's going to be helpful to work with a so-called Lagrangian function. So this Lagrangian function is a function of x and lambda, which basically is my function that I'm going to multiply, plus lambda times, well, this is actually the constraint that we need to satisfy. Because then, what you then see, if we look for stationary points of this Lagrangian function, so the points where the derivative with respect to x and with respect to lambda are both 0, that's a stationary point, so an optimal location, an optimal setting for x and lambda. We see that such a stationary point of my Lagrangian function satisfies my original constraint, right? Because if this is satisfied, so let's say the derivative of x of this Lagrangian function, then this means I'm obtaining this criterion, right? The derivative with respect to f gives me the gradient of f plus lambda times the gradient of g of x. So that really results in this particular constraint. And if we find a solution for the second thing, so the derivative to lambda of my Lagrangian function, then this really implies that my constraint really, the constraint is satisfied, because the derivative of my Lagrangian with respect to lambda will give me g of x minus c, which we set equal to 0, so that defines a stationary point, and that gives me this equation. So we see we can introduce a Lagrangian function, and if we find an optimal location in this Lagrangian function with respect to x and lambda, we have solved our constraint optimization problem. Okay, so it's probably helpful to take a look at some concrete example. So the situation is as follows. So we're set out to maximize this function of two variables, a function of x1 and x2, and it looks like this. And it's graphically depicted over here with these blue contours. And then we have this constraint, which is encoded as follows. So we have the constraint that x1 plus x2 minus 1 should equal to 0. So again, let's make this drawing. So f of x is the function that we want to optimize, and we see immediately for x1 and x2 equals 0, then this thing is maximal, right? Because for every deviation from 0, this thing will get smaller. So this function is concentrated around 0. So let me make again the same drawing with these sort of density plots. Okay, so darker means a higher value, right? So this red-orange colored plot represents my function that I want to optimize, and really the optimal location is right at the point x1, x2 is 0, but we're not allowed to select this point because we need to find points that lie on this constraint surface or this constraint level set. And so this level set is obtained by taking a look at g of x1 and x2, right? So let me also make a plot of that. So this g of x is really a linear function, right? Which has a certain direction. So along this direction, we have an increase of g of x. So the gradient of, so this is the gradient of g always points in this particular direction. And let's again take a look at this intuition of Lagrange multipliers. So the gradient of f points in this direction, so that actually means if I select this point, I could still improve my function values f by moving in this direction. I'm not fully allowed to move in this direction, but I am still allowed to move along this this level set. So basically the next optimal point will be this thing. And if I look at this location, my gradient points somewhere in this direction. So I still have this component along my level set, which allows me to move in this direction. But really at some point, my gradient points in the same direction as the gradient of my constraint function.
And then there's no way that I can improve my function values f anymore by moving along this line. So this is again a recap of really this constraint, right? So we just again showed that at such an optimal location, the gradient of x is aligned with the gradient of g with some multiplier lambda, because delta g and delta f are not necessarily the same, so they can have different lengths and different signs, but at least their directions are the same. So there exists such a lambda for which these two gradients are the same. So that was the principle of this method of Lagrange multipliers. So we define then this Lagrangian function, because then if we compute the stationary point of this function, we actually found our solution. So this is the Lagrange function that we're now going to define, where this thing over here is my function f of x1 and x2. And this thing over here is lambda times g of x minus c, but c is 0 in this example, right? So this is then my Lagrangian function. And then we're going to look for the optimizers of this function. So we take the derivative with respect to x1, x2, and lambda, set it to 0, and then solve this system of equations for x1, x2, and lambda. Okay, so let's do this. The derivative with respect to x1, we see an x1 over here, so that gives me minus 2x1. We see an x1 over here, the derivative will give me plus lambda. So this directly tells me that x1 is going to be lambda over 2. The same here in the x2 case, we find this equation. If we solve it, we get x2 is also lambda over 2. And if we take the derivative with respect to lambda, so that gives me this constraint function really, we can now fill in the x1 and x2 that we just derived. And that tells me that lambda equals 1. Okay, so this tells me that the optimizer of this constraint optimization problem is given by the following. So x1 takes on the value a half, x2 takes on the value a half, and this lambda was used as an aid in deriving this solution essentially. Okay, so that describes the method of Lagrange multipliers for solving constraint optimization problems. So the recipe is define the function that you want to optimize, and also write your constraint in the following formula as a function g of x equals some c, and then with this you can define such a Lagrangian function, so f of x plus lambda times g of x minus c. And once you have defined such a Lagrangian function, then only thing that is left is look for the stationary point. So set the derivative of x to 0, set the derivative of lambda to 0, solve it, and that will give you your constraint solution. In this video, we are again going to adopt a probabilistic viewpoint on machine learning, now in the setting of unsupervised learning via latent variable models. We are going to assume that the data is distributed via a mixture of Gaussians, and it turns out that with such a viewpoint on the data distribution, we obtain a probabilistic variation of the k-means clustering algorithm. Now the idea is as follows. So we have this data, unlabeled data, so we only have measurements x, but we assume they are distributed via some probability distribution that is composed out of a mixture of Gaussians. Like some points come from one of those Gaussian distributions which have a certain mean and variance, and some points come from another distribution. And now we're going to model this in the generative setting. So recall from the classification videos that this generative modeling is the broadest class of probabilistic modeling, right? Because it the goal is to end up with a model for the probability distribution from which these data points x are drawn. So that means once I have such a description of the probability distribution, I can generate new data samples. So that's the generative aspect of things. But we also have been obtaining such models via marginalization process. So we assume that there is such a latent variable, so the three different classes, and then my probability distribution over x is obtained by marginalizing out this latent variable z. And what we did so far is we factorized this. So we said that this joint can be obtained by the product of these latent variable conditional distributions. So what is the probability of observing an x if I know that I'm looking at my latent variable z, times the prior or the probability for observing any of such z at all. And note that this is similar to what we've been doing in the classification case, right? Where we also worked with such class conditional distributions. So the probability of observing a particular X, if I know that this data point came from the class, Z in this case, in combination with a prior probability for observing that particular class at all. Now we work in the unlabeled data setting, so we do not really know which classes there are, but we're just going to assume there is such a ordering or structuring in my data, where each data point came from one of the latent variables, and maybe some of those such latent variables are more likely to occur than others. So we make the splitting as follows. So these would be my latent variable conditional distributions, and this would be the prior for the latent variable. And then, just as in the classification case, once we have obtained such a latent variable conditional distribution and we have these latent variable priors, we can obtain via Bayes' rule also the posterior probabilities for observing this latent variable given my observation X. Okay, now let's go over what I just described, but now graphically. So first of all, this is our data. So we have all these measurements X without any label, any information on the latent variable. So we just color coded here in purple or pink. So these are just my data points, but I'm going to make this modeling choice, right? I say that this data actually comes from such a joint distribution of a point X and a particular latent variable Z. So that's essentially, so we say that in this plot, the data comes from my distribution P of X, but we make this a breakdown. So we say that actually we're observing a data point X together with their latent variable class, which is drawn from this joint distribution. So whenever we observe a data point, we think of it as it actually belongs to a particular class. So the blue class, for example, or it belongs to the green class. So every time I observe a data point X and actually also maybe such a latent variable. So that's color coded here, a point with a color. But then when we do this marginalization, we discard this color or this latent variable, and we just end up with these points. So that's sort of a modeling approach. And then we split this joint probability distribution into these latent variable conditional distributions and, well, the prior for that latent variable, where my latent variable distributions are assumed to be Gaussians with a certain mean and a certain standard deviation or a covariance matrix. And then we assume a Gaussian distribution for each of these latent variable classes. So what's indicated here in blue is basically saying a data point blue is drawn from this class conditional or this latent variable conditional distribution. Let's say Z is blue. So really what this says, it says that my final data distribution is obtained as a mixture of Gaussians, right? Each Gaussian has its mean and covariance matrix. So those are these conditional probability distributions. And we are weighting these distributions with a particular probability for observing that particular latent variable. So these will be called the mixing coefficients in the end. And these are my Gaussians. So that gives a Gaussian mixture model. Okay, and then because we adopt such a generative model, we can also infer the posterior probabilities of observing a particular data point set, right? So that's color coded here. So these are the posterior probabilities from my latent variable given my observation X. Meaning if I observe a particular X, I can check for the probability that it belongs to Z is 1, Z is 2, or Z is 3, and I'm going to color code that in this particular plot. So if a point clearly came from the blue class, it's colored blue. When it came from the green class, it's green, according to my probabilistic model. But when I'm uncertain, I'm going to mix these colors. Like I'm going to mix the ink that sort of generated these colors. So that's graphically depicted over here. So in essence, this is a sort of a soft version of the k-means clustering method, right? Because now if I have a new data point, I assign a probability of it belonging to one of the classes. I'm not going to say this belongs to the blue class. I'm just going to say with this probability, it belongs to the blue class. Okay, so that's the setting of this Gaussian mixture model. We can use it to model our data distribution and then run it in the generative setting to generate new data points that sort of follow the distribution that we have been observing so far. But we can also use it
for, let's say, cluster assignments in a soft probabilistic way. Okay, so then essentially what we're doing is we made these observations of these data points, and then we're going to model the distribution that may have generated this data point, right? So we are going to parameterize our probability distribution in the following way. So, well, that's just explained. So we explain this with a Gaussian distribution, and this with just a probability, just a number for observing this particular latent variable. And I'm going to describe in detail how we're going to model these distributions. But once we have such a model for the distributions, we can of course maximize the likelihood of my distribution actually describing this data. So again, once we have a probabilistic model, we can optimize it. So we can tune all these parameters via the maximum likelihood approach. So that's really the principle that we're going to stick to. And that's what we're going to do again today. So we're constructing this probabilistic model P of X. And we're going to model these conditionals with Gaussians and these distributions essentially with generalized Bernoulli distributions, just like we've done before also in this generative classification setting. Okay, so let's go over our modeling approach. First of all, we assume that we're dealing with discrete latent variables, which really means that I'm going to assume that there are only k clusters or k classes that describe my model. I'm going to factorize my distribution with only k, in this example, 3 different classes. That is what it means. So this is a discrete variable that only can take on the value 0 or 1. So my data point can only belong to one of these clusters. Right, so then I need to describe this probability distribution for the probability that my data point belongs to this particular class, meaning that zk equals 1. And I'm going to model that with just this number, like we've done before in the classification setting. So this pi k is really the probability of observing my kth class. Okay, so this number should represent a probability, so it should take on a value between 0 and 1. And also, because we consider this as a probability, the sum over all my k classes should equal to 1, right? So this really imposes a constraint, which we have to deal with later on when we actually start to optimize for these particular values pi k, because these are now my model parameters, right? Then I'm going to model the clusters with Gaussians, meaning that these cluster conditional distributions are going to be modeled with Gaussian distributions. Again, so these kind of distributions are going to be modeled with Gaussians, and each Gaussian has a particular mean and it has a particular covariance matrix which defines the shape of this distribution. And of course then with these two modeling choices together, so we have a prior and these cluster conditionals, we can obtain the joint probability distribution for observing an X together with a particular cluster label or value for the latent variable. So it's going to be the product of my cluster or latent variable conditional distributions, which we modeled with a Gaussian, and then the product with these priors, which we modeled with these numbers pi k. And then with these two components, we have everything in place to construct a generative model, right? So in the end, we were modeling our distribution for the data point X, which can be obtained via this joint probability for X with the latent variable, the unobserved latent class, let's say, via this marginalization process, right? So we can run this in the generative setting, and let me explain what I mean with that. So we can generate new data points by first drawing a latent variable according to my prior distribution, which I'm now modeling. I have these pi k's. So with probability pi k, I select, well, the kth cluster. Then I'm going to use this kth cluster to generate a new data point given my cluster conditionals or my latent conditional points. And that then would give me a point somewhere, well, in line with the distribution that I had observed so far. So running this in a generative setting would mean I randomly pick a color according to my priors, a blue, green or red, and then suppose I pick the red point, and then I'm going to generate a data point according to my Gaussian distribution, and it gives me a point maybe somewhere over here. So then we generated a new data point. Okay, so that explains the generative aspect of things.
but maybe we are also interested in inferring the posterior probabilities for my latent variable. So this is actually inferring the latent cluster, meaning that if I made an observation for a point X, I can assign probabilities to this point belonging to one of these unobserved clusters. And this follows from Bayes' rule, right? So we have this cluster conditional times the prior divided by the evidence, so my marginalized distribution. So if you write this out, it's as follows. So this P of X can be obtained via the marginalization over my clusters. So now here indexed with a J. So this is actually my joint probability distribution factorized in these two components. So, and if we then insert our modeling choices, so we said the priors were modeled with some number pi k, and the conditionals were modeled with Gaussian distributions, then this is really the formula for obtaining my conditional, my posterior probability for, well, my observed data point X belonging to one of the latent clusters. And for convenience, really, we're going to introduce this new symbol, gamma. So this gamma will be called the responsibility. So really the responsibility that class K takes for explaining data point X. Okay, so that's a symbol that we introduced now. This gamma zk is essentially the posterior probability for my kth class given my observation X, and it will be called the responsibility that my kth class takes for explaining data point X. And in a way, it's something like this. When I observe a new data point X, if it's close to point blue, then the blue class is pretty certain and says, yeah, I'm pretty sure that this belongs to my class, so I take this high responsibility for this point. But if my point is somewhere between classes, then both classes produce a low posterior probability, and in that sense take a low responsibility for this particular point. But either way, this name responsibility really refers to the posterior probability. Okay, so we have such a probabilistic model, and we have observed our data points, right? And well, we can model now my distributions, with these pi's and the mu and the sigmas of my Gaussian distributions. But I still have to set those, right? So I have this probabilistic model, and now I want to infer what parameters are most optimal, which parameters lead to the distribution that most likely explain my data. So with this in place, I can define the log likelihood, and we're going to maximize this in order to find the optimal parameters that describe my data. So we've done this many times before. So we define a probability distribution, we have our data, so we can define the likelihood, and we can define the log likelihood. So we make this IID assumption again, that each data point was drawn from the distribution that we're actually modeling. So then we can make this factorization over all my individual data points. Now, the log of this factorization results in the sum of all these log likelihoods for the individual data points. But now things get tricky because so far our distributions were relatively simple. It was just an exponential or some other distribution, and then the log of this thing gave us something nice. But now we're considering this mixture of Gaussian. So actually we have to take the log of a sum of different components. And this is something that we can no longer analytically write out. So really, because of this sum over here, the log of the sum of these components, I cannot further, let me write it down. I cannot further simplify this because of the sum. So what now? How are we going to maximize this log likelihood? Now we're going to do this via the expectation maximization algorithm. So we're going to iteratively improve our log likelihood, and I'm going to explain that in the upcoming slides. Okay, so this is what we're set out to do. We're going to maximize the likelihood with respect to my model parameters. And so this is the likelihood, the log likelihood actually. So let me write this down. This is the log of the likelihood of my entire data set. So I'm going to abbreviate it with P of capital X. And what we've been doing so far, we maximize this by looking for the stationary points of my log likelihood.
And that means that if I, for example, want to optimize with respect to my parameter mu k, I take the derivative of mu k of my log likelihood and set it to 0 and then solve it for mu k. But now, because we have this complicated expression, so the log of the sum of all these components, I can no longer find a nice expression for mu k, because if I take this derivative, I still have something that depends on all my other parameters. But what I could do, and this is the trick behind the expectation maximization algorithm, I can write my solution for mu k, so, well, it is some expression, and I'm going to keep it still as a function of these responsibilities, z and k. So that's the essential approach behind this. So I cannot find a nice closed form solution for mu k, because this, if I take this derivative, set this to 0, solve it for mu k, I still have something which depends on mu k, sigma k, and the other parameters. But it turns out that we can group all the remaining parameters into this responsibility term. So this responsibility term still depends on my other parameters, so on pi k, on even on mu k, and the sigma k's. But what I'm going to do in this expectation maximization algorithm, I'm going to fix these posterior probabilities or these responsibilities, and then solve for my mu k's and all the other parameters. So and then I have obtained these new parameters, I can update my responsibilities, and then again iterate this solution, this maximization step, and solve for the parameters. And I think in the upcoming slides it will become clear what I actually mean with this derivation step and how this scheme works. But the general structure is we can eventually find local minima of this highly non-convex optimization problem by alternating the following steps. So we can update the expected posterior. So this isn't our final posterior yet, but we call it the expected posterior. So given my current parameters, I can evaluate these posterior distributions or these posterior probabilities. So that's like an assignment step, right? Each data point is assigned to one of the k classes via these posterior probabilities. And then once we made this assignment, we can actually just fill in the solutions that we derive from mu k as a function of these posteriors, as a function of these responsibilities. And that gives us the pi k's, the mu k's, and the sigma k's, so my model parameters that maximize my log likelihood for a fixed posterior. So in a bit more detail, the expectation maximization algorithm is as follows. So I said we are going to maximize the log likelihood. This log likelihood is a complicated function because if we adopt the strategy that we've been doing so far, let's look for stationary points, then we cannot find a closed form expression for mu k, but we find something that depends on these gammas, on these posteriors. Now, this is a preview of what is coming up. So I am going to derive how to obtain these mu k's, these pi k's, and how to express this in terms of these gammas. But this is a preview that shows that we can actually find these mu k's in terms of this gamma. The same for the sigmas. So we are able to find such expressions. So that means that we can actually iteratively update our model parameters. So once we know, once we have evaluated our posterior distribution, so once we have made this assignment during the expected step, we can update our model parameters, mu k, pi k, sigma k. And once we have updated our model parameters, we can update our posteriors. And we keep on iterating this. And this actually gives us then an algorithm which is very similar to what we've been doing in the k-means clustering algorithm. And it is as follows. So we first initialize the pi k's, the mu k, and the sigma k. So let's just initialize it with just some random mean and some isotropic covariance matrix. Okay, so then with these initial parameters, I can perform the E step. I can update the expected posterior. So I can update the expected posterior, gamma, z, and k. So this gamma refers to the posterior probability of a data point x belonging to that particular class, right? So that's color coded here. So we can make these soft assignments with a certain probability let's say this point belongs to the blue class, and also with a certain probability it belongs to the red class. And in this particular case we get a sort of mixing of these colors because there isn't a very strong assignment that we can make. Okay, so now we have updated our gammas, and once we have done that, we can move on to the maximization step. So the step that actually maximizes my log likelihood via the following update rule. So that's the maximization step, which basically says that I'm now going to find my new model parameter, so the mean of my Gaussian distribution and its covariance matrix, such that it is most likely describing this particular set of points that are probably belonging to the blue class. Okay, so then we have these new model parameters. Then again, we can update our posterior probabilities of a particular data point belonging to this class. And that gives me this new expected update step, right? And then with these new gammas, I can again obtain my new model parameters in this maximization step. And then I'm iterating this expectation maximization steps until I converged to something nice. And at this point, it's maybe worthwhile to point out that this expectation maximization algorithm for Gaussian mixture models is actually much slower than the k-means clustering, because here only after 20 of such iterations I am able to find a configuration that doesn't change anymore between succeeding steps. Now I'll get back to this point of slow convergence later on, but this essentially described the expectation maximization step. So this was a preview, and I haven't really showed how to derive this maximization step, how to derive these expressions. So that's what I'm going to do next. So we're set out to maximize the log likelihood. We take the derivative of this thing, set it to 0, and then define our solution in terms of these posterior probabilities. And I'm going to start off with deriving this expression for mu k. So let's do that. And before we get there, I want to make this following remark, which is a recurring thing in the upcoming derivation, that, well, first of all, we are working with multivariate Gaussians to model our conditional distributions. So for a given class k, I model the probability of observing an x with such a Gaussian. And now I'm going to take the derivative with respect to mu k of this Gaussian. And really here I want to show that the derivative of such a Gaussian is again a Gaussian multiplied with this front vector, with this particular vector. And you can imagine where this comes from, right? Because this Gaussian is this exponential, and the derivative of an exponential is the exponential itself times the derivative of the things inside the exponent. So that leads to the fact that I'm seeing this Gaussian again. That's because of the exponent. And then we have this term over here, and that's because of the derivative inside the exponent. And this follows from taking the derivative delta mu k of a half x minus mu k transpose inverse covariance x minus mu k. And we've computed these derivatives before in the exercise classes. So essentially this derivative is given by a half times x minus mu.
In the previous videos we covered unsupervised learning with discrete latent variable models. In the upcoming videos we will consider continuous latent variable models instead. And before we move on to a full probabilistic interpretation of such models, we start off with a non-probabilistic version of it. Today we will talk about principal component analysis. It is a method for dimensionality reduction which can be derived via several principles. Now in this video we will derive principal component analysis via a maximum variance formulation, and in the next videos we will derive it using a minimal reconstruction error viewpoint and a probabilistic viewpoint. Now the main goal of such continuous latent variable models really is dimensionality reduction. So the goal is dimensionality reduction, where we treat our data. So our data lives in a high dimensional space. For example, my image can be of 100 by 100 pixels. But we're going to assume that actually the true underlying data structure is of lower dimension. And maybe this is best explained by an example such as the following. So let's say we are observing these images of a tree, and this tree is generated by well, by shifting it, so by translating it a little bit to the right or to the top, rotate it a little bit. So we have all these images that represent a tree, and this tree is rotated and translated. Now, the images in itself are high dimensional, right? So they're 100 by 100, so let's say 10,000 pixels, and each pixel value can take on really any value on the real line. But so if I were to generate one random image, I would have so many possibilities for, I could pick a value for each of these 10,000 values. So that's what we see. We see all these images consisting of these 10,000 pixel values, but we see a lot of similarities between these images, right? And now, especially in this particular case, once you realize that all these images are a tree, it's just that they're translated and rotated, this actually means that if I have one core representation, this particular tree, then actually my latent space only consists of 3 parameters. So that will be the two translation parameters and 1 rotation parameter. So if I have this core representation of the tree, then I can generate any of these images with just 3 values. Now that's the idea about dimensionality reduction. We assume that there is such a structure that actually my data comes from a lower dimensional space, and what we observe may be high dimensional, but intrinsically it's of low dimension, and we want to recover this particular manifold or this particular low dimensional description of the data. Now, of course, this is a very simplistic example, right? But the idea of such lower dimensional manifolds, it makes sense and it works in a lot of applications. But if we stick, for example, to this digit recognition example, we could consider the latent space to be much bigger, right? There's so much variations that take place. We could consider scaling, for example. We could consider not just the digit tree, but all digits 0 to 9. We could consider different colors and different handwriting styles, and this goes on, right? But still, even if you consider all those variations that you can expect, then it's very probable that the number of latent variables will still be much fewer than the 10,000 dimensions that my images really have. So the size of this vector space. So it makes sense to proceed into this direction of dimensionality reduction, right? Now, in this example, the latent space is a nonlinear transformation of the image, right? Because I cannot just transform like a scaling parameter in one step to an image. It probably is a very complicated model to do so. But in principle, this is how we could treat it. So we're searching for this latent subspace, which we can then transform to our final observation. So these actual digits via some model. And this model can be highly nonlinear. Maybe that I'll cover that a little bit in video 10.4. But for now, we really stick with latent variable models that represent a linear embedding of my data. And later we consider the generalizations to the nonlinear case. So that's what we're going to do. We're going to find a linear projection of the data, and we're going to do it in such a way that the variance of this projected data is maximal. So what we're essentially after in this principal component analysis framework with this maximum variance approach is that we have this high dimensional data, so we have points in a high dimensional space, and we observe variations in several directions. And our task is to recover these principal directions, these principal component among which the variation is maximal. So the idea is that we, for example, measure high dimensional vectors. I can only draw this in 2D now, so 2 is high dimensional in this case. So we have all these measurements, and we want to reduce these 2D measurements to just a 1D component. So what we're going to do is we're going to look at the axis of maximal variation. For example, if I take a look at this data, it's elongated in one structure, so we have a lot of variation in this direction, little variation in this direction. So if I'm going to make a projection, it's best I do it along this direction, and maybe not so relevant to do it along this direction. So our objective now is to recover these axes of maximal variations, and these axes will be called principal components. So this is again summarized over here, maybe now in a bit more detail. So I have this data set of points, these observations which lie in some d-dimensional space. Again, here's a 2D visualization. So these are my 2D observed data points. And now I want to project this to a lower dimensional space. So I want to project it on this line. So now a 2D point is represented with a 1D point somewhere on this line. And these projections will be done via orthogonal projections, right? So if I have this data point, I look for the closest point on this direction, on this line, and that will be my new embedding. And then my objective is to find this direction among which the variation in my point is large. So if I look at this, I have variation is large. And of course, this is a relative notion of variance. So let me pick another direction to compare it with. Suppose I picked this direction. So this would have been my U1. Now, if I project the points to this particular line, then this point ends up over here, this point somewhere over here, this one over here, this one over here. Then along this line, I actually have a smaller variation in comparison to the projection to this purple line over here, indicated in green, this variance. So my objective now is to find a direction, U1, that results in a maximum variance of the projected points onto this line. Okay, so that is going to be my objective. And then instead of, so now this was a 2D to 1D mapping, an example, but in general we consider d-dimensional data points, and we're going to project it to m-dimensional hypersurfaces or lower dimensional spaces, where m is assumed to be given. And now, before we proceed, I just want to recap some basic definitions that we've seen many times actually. So the mean is defined as follows. So we indicate it with an overline x. So that will indicate the mean over all my data points. And then we have a covariance matrix obtained in the following way. And such a covariance matrix is then given to be symmetric and positive definite. And these are some properties which we will use later on. Okay, now let's try to build this up from simple concepts. And we start off with a 1D projection. So my data is d-dimensional, and I want to project my data now onto this one-dimensional line using this as a direction vector. Then the projection of such a data point onto this vector, so is simply given by taking this inner product, the scalar product. This essentially gives me a single value, right? It gives me a scalar value, which I'm going to denote with zn1, and it's just a single value. Okay, and then we can also obtain the mean of all these projections simply by projecting the mean itself. And this actually directly follows from linearity of the mean. And with this I mean if I take the expectation over my new projected values, I could do that by, of course, taking the expected value over these projections. But by linearity of this expectation, I can take this projection vector outside and order it in the following way. So you see, we can also first compute the mean of my data and then project it. Okay, but that's just a useful property. So what we're really after was this direction vector u1, and also really the length of a direction isn't too important. Actually, we're only interested in the direction itself, right? So we're going to search for direction vectors u1 which have a length 1. So we normalize this direction vector. Okay, so the objective is to find the vectors u1 that really result in a projection with maximal variance. So let's take a look at the variance of the projected data. So the variance of this projected component. Okay, so that's given here, right? So the average over the square distance of each projection to its mean. And we can see we can write it out into a convenient form. So first, by starting off recognizing that this u1 can be factorized in the following way. So then we have this form. And if we then write it out, so we expand the square, we see that we can write it in the following way. Because this is a scalar product between two vectors, and I can change the order by putting a transpose and moving this to the left, put a transpose there, and that gives me this term multiplied with, well, the term that I already have. So this is nothing else as rewriting. And then because these u1s do not depend on my index n, I can pull this sum inside, and that gives me the following. And